On the 6th of December 1972, at precisely 12:33 in the afternoon Eastern Standard Time, 3 men strapped inside a cone of aluminum and steel felt the entirety of human civilization fall away beneath them. The Saturn V rocket that carried Apollo 17 toward the moon generated 7.6 million pounds of thrust at liftoff, enough force to compress the astronauts' chests against their couches, with a pressure that made breathing an act of deliberate will. Commander Eugene Cernan, Lunar Module pilot Harrison Schmitt, and Command Module pilot Ronald Evans watched through their tiny windows as the Atlantic Ocean shrank from a heaving expanse of water into a curved blue line, then into nothing more than a patch of colour on a sphere that itself was shrinking with every passing second. They were leaving Earth. They were leaving every human being who had ever lived, every city that had ever been built, every war that had ever been fought, every love letter that had ever been written. They were carrying with them the sum total of human experience into a void that cared nothing for any of it. 3 days later, on December 10th, Ronald Evans entered lunar orbit while his crewmates descended to the surface in the Lunar Module Challenger. What happened next has not been repeated in more than 50 years. Evans, alone in the Command Module America, swept around the moon's far side and became one of only 24 human beings in all of history to witness with their own eyes the hemisphere of the moon that never faces Earth. He saw craters that had never been photographed at close range, mountain ranges that cast shadows across basins older than life on our planet, terrain so ancient and so untouched that the footprints of the cosmic bombardment that shaped our solar system remained preserved in perfect silence. He described what he saw into a tape recorder, his voice the only human sound in that absolute darkness, and when America swung back around the lunar limb and re-established radio contact with Earth, those descriptions became the last first-hand human account of the lunar far side that anyone would hear for half a century. That half-century ends now. In the coming months, 4 astronauts aboard the Orion spacecraft will retrace a path no human crew has flown since the Apollo program concluded. The Artemis II mission will carry Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Canadian Space Agency astronaut Jeremy Hansen on a trajectory that swings around the moon and returns them to Earth across a span of approximately 10 days. At the moment of closest approach, when Orion passes behind the lunar far side and radio contact with Earth is temporarily severed, these 4 individuals will see something that no living human being has witnessed with their own eyes. They will look out through the windows of their spacecraft at a landscape that exists in photographs, in orbital data, in the mathematical models of planetary scientists. But that has not been observed directly by any member of our species since Ronald Evans made his final orbit on December 16th, 1972. This is not simply a ceremonial return to a place humanity once visited. The moon we are returning to is not the moon we left. 5 decades of robotic exploration, orbital mapping, and ground-based observation have transformed our understanding of the lunar far side so completely that Cernan, Schmitt, and Evans would scarcely recognize the scientific questions we now carry with us. The craters they glimpsed through their windows have been measured down to the centimetre. The composition of the rocks they could not reach has been analysed through spectroscopy. The gravitational anomalies they flew over without understanding have been mapped with such precision that we can now model the interior structure of the moon to a depth of hundreds of kilometres. And yet, for all this accumulated knowledge, the far side of the moon remains one of the most enigmatic surfaces in the solar system. We know more about it than any previous generation of scientists could have dreamed possible. We understand less about it than our confidence would suggest. If you want to discover exactly what Artemis II will encounter when Orion sweeps behind the moon, to understand why this 10-day flyby carries scientific implications that extend far beyond the moon itself, and to follow along as data arrives in real time from a vantage point no living human has occupied, then please consider liking and subscribing. It truly helps more than you know. Are you ready? Let us begin. The far side of the moon earned its mystery through an accident of celestial mechanics so old that the sun was still young when it occurred. When the moon formed approximately 4.5 billion years ago, likely from debris ejected by a collision between the proto-Earth and a Mars-sized body called Theia, it began its existence much closer to Earth than it orbits today, and spinning much faster on its axis. In those early epochs, The Moon completed a rotation in a matter of hours rather than the 27.3 days it requires now. Earth would have appeared to rise and set across the lunar sky just as the Sun rises and sets across ours, and every portion of the lunar surface would have experienced its light. But the same gravitational forces that created ocean tides on Earth also created tidal bulges in the solid rock of the Moon, and these bulges dissipated rotational energy through friction. The Moon slowed. Year by year, millennium by millennium, eon by eon, the lunar rotation rate decreased while the Moon simultaneously spiraled outward from Earth at a rate of approximately 3.8 centimeters per year. Eventually, inevitably, the Moon reached a state of synchronous rotation, where the time it takes to complete one orbit around Earth exactly matches the time it takes to complete one rotation on its axis. This condition is called tidal locking, and it means that the same hemisphere of the Moon perpetually faces Earth while the opposite hemisphere perpetually faces away. The process required hundreds of millions of years to complete, but once it finished, it created a permanent division in how humanity would come to know its nearest celestial neighbour. One hemisphere became the near side, visible from every point on Earth's surface that could see the night sky, studied by astronomers since before the invention of the telescope, mapped in such detail that every major feature acquired a name. The other hemisphere became the far side, hidden from every eye that ever looked upward, unknown and unknowable until the space age made it accessible. The distinction matters far more than simple visibility. The near side and far side of the Moon are geologically, compositionally and structurally distinct in ways that continue to puzzle planetary scientists despite decades of intensive study. The near side is dominated by the dark, smooth plains called Maria, which is Latin for seas, because early astronomers mistook these expanses of solidified lava for bodies of water. The Maria cover approximately 31% of the near side surface, filling the floors of ancient impact basins with basaltic rock that erupted from the lunar interior between 3.9 and 3.1 billion years ago. They give the near side its familiar face, the pattern of light and dark that humans have interpreted as rabbits, faces, and countless other figures throughout recorded history. The far side has almost no Maria at all. When the Soviet Luna 3 spacecraft transmitted the first photographs of the lunar far side back to Earth on October 7, 1959, scientists expected to see a mirror image of the near side, more dark Maria scattered among bright highlands, more of the same face they had known for millennia. What they saw instead was a surface almost entirely covered in bright, heavily cratered terrain, with only two small mare patches visible in the entire hemisphere. The asymmetry was so striking, so unexpected, that many researchers initially suspected the photographs might be flawed. They were not. Subsequent missions confirmed that the far side of the Moon is fundamentally different from the near side, and explaining that difference has occupied planetary scientists ever since. The most prominent feature on the lunar far side is the South Pole Aitken Basin, and it is not an exaggeration to say that this single impact structure has driven more lunar science questions than perhaps any other feature on any body in the solar system. The basin stretches approximately 2,500 kilometres from rim to rim and plunges nearly 8 kilometres below the surrounding terrain at its deepest point, making it one of the largest and oldest impact structures anywhere in the solar system. It formed approximately 4.3 billion years ago, during a period called the Late Heavy Bombardment, when the inner solar system was swept by a rain of asteroids and comets that left scars on every rocky body that survived the cataclysm. The object that created South Pole Aitken was enormous, likely more than 200 kilometres in diameter, and it struck the lunar surface with enough energy to excavate through the entire thickness of the lunar crust and into the mantle below. The consequences of that impact should have been spectacular. An impact of that magnitude should have generated enough heat to melt thousands of cubic kilometres of rock, creating a vast magma ocean that would have filled the basin floor with volcanic plains similar to the Maria on the near side. And yet the South Pole Aitken Basin contains remarkably little volcanic material. Its floor is composed primarily of highland-type rocks, minerals that originated deep in the lunar crust, or even the upper mantle, brought to the surface by the violence of the impact itself, but never buried beneath later volcanism. The basin exists as a window into the deep interior of the Moon, a place where materials that normally lie hidden beneath hundreds of kilometres of rock are exposed at the surface, accessible to observation, and eventually to sample collection. Artemis II will not land on the Moon. The mission profile calls for a lunar flyby, a trajectory that carries Orion around the Moon and back to Earth without entering lunar orbit or deploying any crew to the surface. This limitation might seem to render the far side observations merely ceremonial, a symbolic return rather than a scientific one. That interpretation would be mistaken. What Artemis II will achieve during its passage behind the Moon represents an opportunity that no previous human mission has possessed. The chance to observe the lunar far side with modern instruments, modern communication capabilities, and modern understanding of what questions most urgently need answers. The Orion spacecraft carries a suite of cameras capable of resolutions that would have seemed miraculous to the Apollo astronauts. The optical navigation cameras designed to help Orion navigate autonomously can also be pointed at the lunar surface to capture imagery at wavelengths and sensitivities unavailable in 1972. More importantly, Orion carries something the Apollo command modules never had: the ability to record and store data during the communication blackout period when the spacecraft passes behind the Moon. When America swung around the lunar far side, Ronald Evans could describe what he saw into a tape recorder, but the scientific instruments aboard his spacecraft were limited to what 1970s technology could provide. The radiation monitors, the cameras, the limited sensors available could not approach the capabilities of instruments designed half a century later with the accumulated advances of the digital revolution. The scientific community has identified specific observation targets for Artemis II's far side passage, and the list reveals how dramatically our questions about the Moon have evolved since Apollo. Among the highest priorities is direct observation of the interior of the South Pole Aitken Basin, particularly the regions where orbital spectroscopy has detected anomalous mineral signatures. These anomalies include concentrations of iron and titanium oxides that do not match the expected composition of either crustal or mantle materials, suggesting either that the impact excavated materials from depths greater than our models predict, or that the lunar interior contains compositional variations we have not yet explained. Human eyes observing these regions in real time, supplemented by camera systems recording at multiple wavelengths, could provide context that orbital data alone cannot supply. There is also the matter of the far-side craters themselves, which differ from near-side craters in subtle but scientifically significant ways. The bright rays that extend outward from young impact craters, formed when the impact ejects fresh material across the surrounding terrain, persist longer on the far side than on the near side. This difference results from the far side's isolation from the effects of spacecraft exhaust, human activity, and the minute but measurable contamination that near-side operations have introduced over 60 years of lunar exploration. The far side preserves the record of recent impacts with a fidelity the near side cannot match, and that record contains information about the current bombardment rate, the composition of impacting objects, and the ongoing resurfacing processes that continue to modify the lunar landscape. But the most scientifically charged question that Artemis II may illuminate concerns not the surface of the far side, but what lies beneath it. In 2019, researchers analysing data from NASA's Grail mission announced the discovery of a massive anomaly buried beneath the South Pole Aitken Basin, an excess of mass so large that it could represent the metallic core of the asteroid that created the basin, still embedded in the lunar mantle after 4.3 billion years. The anomaly contains at least 2.4 billion metric tons of excess material, enough to create a layer more than 300 kilometres thick if spread across the entire basin floor. Alternative explanations include dense concentrations of oxides in the mantle rock, remnants of the ancient magma ocean that covered the Moon shortly after its formation, or structures we have not yet imagined. Orion will pass over the South Pole Aitken Basin during its far-side transit. The gravitational influence of the buried mass anomaly, whatever its origin, will create a minute but measurable perturbation in the spacecraft's trajectory. Tracking that perturbation with the precision of modern navigation systems could refine our estimate of the anomaly's size, depth, and distribution, providing constraints that orbital missions alone have not achieved. The human crew aboard Orion will serve as witnesses to this measurement, able to report on instrument readings and visual observations in ways that robotic missions cannot match, and their presence transforms what might otherwise be a routine orbital calculation into a moment of genuine scientific discovery. The far side of the Moon also holds secrets that extend beyond lunar science into questions about the history of the entire inner solar system. The heavily cratered terrain that dominates the far side preserves the impact record of the late, heavy bombardment more completely than any other accessible surface in the solar system. Earth's geological activity has erased nearly all evidence of the bombardment from our planet's surface. The near side of the Moon was resurfaced by volcanic maria that buried the oldest impact craters. Mars has been modified by wind, water, and volcanic activity to the point where its bombardment record is fragmentary at best. But the lunar far side has remained essentially unchanged for more than 3 billion years, a frozen archive of the violence that shaped our cosmic neighbourhood. Reading the archive requires understanding the relationship between crater size, crater density, and surface age. Planetary scientists have developed sophisticated techniques for dating surfaces by counting craters, a field called crater chronology. But the method depends on assumptions about the rate of bombardment over time. If the bombardment rate was constant, then crater counts translate directly into ages. If the rate varied, with periods of intense bombardment separated by quieter intervals, then the translation becomes more complex. The far side of the Moon preserves the baseline against which all other crater chronologies in the inner solar system are calibrated. Every age we assign to a surface on Mars, Mercury, or the moons of the outer planets ultimately traces back to our understanding of the lunar far side crater population. Artemis II will observe regions of the far side that have been imaged only at moderate resolution by orbital cameras. The human visual system, despite all the advances in digital imaging, remains remarkably effective at pattern recognition, at distinguishing subtle variations in texture and albedo that automated algorithms sometimes miss. The astronauts aboard Orion will have the opportunity to identify features that warrant closer investigation by future robotic or human missions to build intuitions about the far side landscape that cannot be acquired from photographs alone. This observational capability is not a minor consideration. The Apollo astronauts consistently reported seeing details on the lunar surface that they had not anticipated from pre-mission imagery, and their observations guided subsequent analysis in ways that remote sensing alone could not have achieved. The communication blackout that occurs when Orion passes behind the Moon will last approximately 47 minutes during each far-side transit. During this period, the crew will be entirely isolated from Earth, as alone as any human beings have been since the last Apollo mission half a century ago. The psychological implications of this isolation have been studied extensively, but the experience itself remains impossible to simulate. No amount of training in a soundproofed room can replicate the knowledge that the entire mass of the Moon stands between you and everyone else in your species, that no signal could reach you if the unthinkable occurred, that you are genuinely beyond the reach of any possible rescue. The Apollo astronauts who experienced this isolation described it in different ways. Some found it peaceful, even transcendent. Others found it deeply unsettling. All of them found it unforgettable. Reed Wiseman, Victor Glover, Christina Koch, and Jeremy Hansen will each confront this moment according to their own temperaments and preparations. They will have trained for years to reach the point of lunar insertion, will have spent thousands of hours in simulators and classrooms and physical conditioning facilities, preparing for every conceivable contingency. And then they will pass behind the Moon, and the radio will fall silent, and they will look out through their windows at a landscape that no living human has seen with their own eyes. What they observe in those 47 minutes will be recorded by the spacecraft's instruments, stored in digital memory until radio contact is restored, and transmitted back to Earth for analysis by research teams across dozens of countries. But the experience of being there, of seeing the far side firsthand, will belong only to them. They will carry it for the rest of their lives, a memory that cannot be fully shared, a knowledge that separates them from every other human being on the planet. The observation plan for Artemis II has been developed in close collaboration with the lunar science community, and it reflects a careful balance between what is scientifically important and what is operationally feasible. The spacecraft will approach the Moon on a free return trajectory, meaning that the lunar gravity assist will automatically send Orion back toward Earth without requiring any additional propulsion maneuvers. This trajectory was chosen for crew safety reasons, as it ensures that even a complete propulsion failure would not strand the astronauts in lunar orbit, but it also constrains the observation opportunities. The spacecraft cannot loiter over specific targets or adjust its path to optimize viewing angles. The crew must work within the constraints of orbital mechanics, observing what the trajectory makes available and accepting that some targets will remain beyond reach. Despite these constraints, the observation windows are remarkable. Orion will pass within approximately 7,400 kilometers of the lunar surface at closest approach, a distance that would be considered extreme in the context of Earth orbital operations, but that places the crew closer to the Moon than any humans have been in more than half a century. At this distance, the far side fills the spacecraft windows, a vast curved surface of grey and white stretching from horizon to horizon. The level of detail visible to the naked eye at this range far exceeds what any telescope on Earth can achieve, as the atmosphere that limits ground-based lunar observation is entirely absent. The astronauts will see shadows cast by crater walls, the subtle colour variations that indicate compositional differences in the regolith, the bright splash patterns of young impact craters superimposed on the darker background of old terrain. They will see the Moon as it actually is, not as it appears through the veil of Earth's atmosphere. The far side terrain they will observe is organised into several distinct geological provinces, each with its own scientific significance. The heavily cratered highlands that dominate most of the hemisphere represent the original lunar crust, formed approximately 4.4 billion years ago, when the global magma ocean that covered the newly formed Moon began to crystallise. The minerals that make up this crust, primarily feldspar in a rock type called anorthosite, are less dense than the underlying mantle, and they rose to the surface like ice cubes floating on water. The resulting crust is thick on the far side, averaging approximately 50 kilometres compared to approximately 30 kilometres on the near side, and this thickness difference is one of the primary explanations for the far side's lack of volcanic maria. The mare-forming lavas originated deep in the lunar mantle, and erupted through fractures in the crust to fill the floors of large impact basins. On the near side, where the crust is thin, the lavas reach the surface relatively easily. On the far side, where the crust is thick, the lavas mostly failed to penetrate, and the ancient highland surface remained preserved. This crustal thickness asymmetry creates a natural laboratory for understanding planetary differentiation, the process by which originally homogeneous bodies separate into distinct layers with different compositions. The Earth differentiated into a metallic core, a silicate mantle, and a less dense crust. But the details of this process remain poorly understood because Earth's geological activity has erased most of the evidence. The Moon differentiated through similar processes, but its smaller size meant that it cooled more quickly, and its geological activity ceased much earlier. The lunar crust preserves a record of differentiation processes that occurred within the first few 100 million years of solar system history, and the far side crustal thickness variations provide constraints on models of how that differentiation proceeded. Among the specific features that Artemis II's observation plan targets is the crater Tsiolkovsky, named for Konstantin Tsiolkovsky, the Russian rocket pioneer who derived the fundamental equation of space travel decades before the first rocket ever left the ground. Tsiolkovsky crater is one of the few far-side craters with a dark mare floor, a patch of solidified lava that somehow managed to reach the surface despite the thick far-side crust. The crater is approximately 185 kilometres in diameter, large enough that the impact excavated through the crust and into the upper mantle, fracturing the rock sufficiently to allow subsequent volcanic eruptions to fill its floor. The presence of mare material in Tsiolkovsky provides a rare window into far-side volcanic history, an opportunity to study volcanic products that formed under different crustal conditions than the extensive near-side maria. The observation of Tsiolkovsky from Orion will complement the orbital data already acquired by the Lunar Reconnaissance Orbiter and other missions, but it will add something that orbital observation cannot provide: context. The human visual system excels at integrating information across large spatial scales, at recognizing patterns and relationships that become apparent only when viewed as a coherent whole. An astronaut looking at Tsiolkovsky from 7,400 kilometers can see the entire crater in a single glance, can perceive the relationship between its floor, its walls, its central peak, and the surrounding terrain in a way that stitching together thousands of individual orbital images cannot fully replicate. This contextual understanding is not superior to orbital data, but it is complementary, and the combination of both provides a richer picture than either alone. Another priority target is the far side area surrounding the von Karman crater, the landing site of China's Chang'e 4 mission. In January 2019, Chang'e 4 became the first spacecraft in history to achieve a soft landing on the lunar far side deploying a small rover called U-22 that has been exploring the crater floor ever since. The landing site was chosen because it lies within the South Pole Aitken Basin, offering access to materials that may have originated deep in the lunar interior, and because the relatively flat floor of von Karman provided a suitable landing surface. U-22's observations have revealed unexpected mineral compositions, including concentrations of olivine and pyroxene that suggest the regolith contains materials excavated from the mantle by the ancient basin-forming impact. Artemis II will pass over the von Karman region during its far-side transit, providing an opportunity to observe from above the same terrain that U-22 has been exploring from the surface. This dual perspective, combining the regional context of orbital observation with the ground truth detail of surface exploration, exemplifies the kind of integrated science that the Artemis program aims to enable. The data returned by Orion will not replace the data from U-22, but it will help place the rover's findings in a broader geological context, revealing how the local features the rover has observed connect to the regional structures visible from orbit. The scientific return from Artemis II's far-side observations will depend critically on the quality of the data the mission collects and the promptness with which that data reaches the scientific community. NASA has committed to making Artemis data publicly available with minimal delay, a policy that reflects lessons learned from earlier missions where delta restrictions limited the pace of scientific progress. When Orion's communication link is restored after each far-side passage, the spacecraft will transmit its recorded observations back to Earth through the Deep Space Network, the array of giant radio antennas that track spacecraft throughout the solar system. The images and instrument readings will be processed, calibrated and archived for access by researchers worldwide. This data pipeline will operate in near real time during the mission, and the scientific community has organized itself to be ready. Research teams at universities and institutions across the United States, Europe, Japan, Canada and beyond have prepared analysis protocols that will allow them to begin examining Artemis II data within hours of its arrival. The first scientific papers based on mission observations could appear within weeks of the crew's return to Earth, a timeline that would have been impossible in the Apollo era when data processing took months and access was tightly controlled. But the scientific analysis will extend far beyond the initial rush of papers. The data Artemis II collects will be studied for decades, mined for insights that cannot be anticipated in advance, compared with future observations to track changes and refine interpretations. The lunar far side will no longer be a place that exists only in old photographs and orbital maps. It will become a place that living human beings have seen, a place that modern instruments have examined, a place whose mysteries have been sharpened into specific questions with specific answers waiting to be found. The moon that Artemis II approaches is not the moon that Apollo visited, but neither is it a wholly different world. The craters that Cernan, Schmidt and Evans photographed still scar the surface, unchanged by the half-century that has passed. The regolith that recorded their footprints still lies undisturbed, preserving boot prints and rover tracks and equipment debris exactly as they were left. The silence that Evans described during his far-side transits, the absolute absence of sound that pressed against his ears like a physical weight, still reigns over the lunar landscape. The moon does not change on human timescales. It is too old, too dead, too removed from the geological activity that reshapes planets like Earth. 1,000,000 years from now, the footprints will remain. 1,000,000,000 years from now, assuming no unusual impacts disturb the sites, they will still be there, fading only gradually as the relentless rain of micrometeorites grinds them slowly into anonymity. And yet our understanding of the moon has changed so profoundly that the 4 astronauts aboard Orion will carry with them scientific questions that the Apollo crews could not have imagined. They will know about the buried mass anomaly beneath South Pole Aitken. They will know about the water ice deposits hiding in permanently shadowed craters near the poles. They will know about the lunar swirls, mysterious bright markings that correlate with local magnetic anomalies, and may record ancient volcanic outgassing or solar wind interactions. They will know about the recent discovery that the moon may have had a magnetic field for far longer than previously believed, maintained perhaps by a dynamo in a now solidified core. They will carry with them the accumulated knowledge of 50 years of robotic exploration, orbital mapping, sample analysis and theoretical modelling, and they will apply that knowledge to the interpretation of what they see. The far-side passage will be brief. 47 minutes is not a long time, hardly enough to count as a visit in any meaningful sense, but 47 minutes of direct human observation, supported by modern instrumentation and recorded for immediate transmission to Earth, could provide insights that decades of additional robotic missions might struggle to match. Human explorers bring judgment, intuition, and the ability to respond to unexpected observations in real time. They can notice something unusual and choose to examine it more closely. They can recognize when an instrument reading contradicts what their eyes are telling them, prompting investigation rather than automatic data processing. They are not better than robots in any absolute sense, but they are different, and the combination of human and robotic exploration has always been more productive than either approach alone. The 10-day duration of the Artemis II mission will include far more than the farside passages, of course. The crew will conduct extensive observations of the near side as well, testing Orion's systems in deep space, verifying communication procedures, and rehearsing the operations that will be required for future Artemis missions that will actually land humans on the lunar surface. But the far side passages will be the moments when the mission achieves something genuinely unprecedented, something that cannot be replicated by any spacecraft currently operating, and that will not be matched until future Artemis missions build on what Artemis II demonstrates. When the first images from Artemis II's far side transit arrive on Earth, they will be greeted by a scientific community that has been waiting half a century for this moment. The pictures from Luna 3 were grainy and indistinct, primitive by any modern standard, but they captivated the world in 1959 because they showed something no human had ever seen. The pictures from Artemis DS will be sharp and detailed, recorded at resolutions that reveal features the lunar cameras could never have detected, but they will carry the same essential significance. They will be new views of an old mystery, fresh observations of a place that has haunted human imagination since the first time anyone looked up at the moon and wondered what lay on the other side. The answers waiting on the far side may not be simple. The lunar far side is not a puzzle with a single solution, but a complex geological system with interconnected mysteries that span the entire history of the solar system. Understanding why the far side lacks Maria requires understanding lunar crustal formation, mantle dynamics, thermal history, and impact cratering mechanics altogether. Understanding the South Pole Aitken Basin anomaly requires understanding giant impacts, planetary differentiation, and the preservation of ancient structures over billions of years. Understanding the far side's role in planetary bombardment chronology requires understanding the dynamics of the early solar system, the origin and evolution of the asteroid belt, and the statistical properties of crater populations across multiple planetary bodies. Artemis II will not answer all these questions. A 10-day flyby cannot accomplish what decades of dedicated surface missions will eventually achieve, but it will begin the process of moving from observation to understanding, from mystery to explanation, from the ancient puzzles that have defined lunar science to the deeper insights that will reshape our picture of how planets form and evolve throughout the cosmos. The far side of the moon has waited 4.5 billion years for someone to pay attention to it. After 50 years of human absence, that attention is finally returning. The countdown continues. The spacecraft stands ready. The 4 astronauts who will become the first living human beings in half a century to witness the lunar far side have completed their training, said their farewells, and prepared themselves for a journey that will separate them from every other person alive. When they emerge from behind the moon and radio contact is restored, they will carry observations that no one else possesses, insights that no instrument has captured, memories that will stay with them forever. The far side is about to reveal itself again, and the science waiting in its ancient craters has never been more urgent. But to understand what Artemis II will truly see, and to appreciate why it matters, we must first return to where our knowledge of the far side began, to the cold mathematics and colder politics that launched the first photographs across 250,000 miles of void, and to the chain of discovery that transformed an invisible mystery into one of the most studied surfaces in the solar system. The story of the lunar far side is not merely a scientific narrative, it is a human narrative, shaped by rivalry and cooperation, by ambition and accident, by the persistent drive to see what has never been seen and to know what has never been known. That story began long before any spacecraft left Earth, and it continues now, in the final preparations for a mission that will write its next chapter. The first human to suspect the moon might hide something worth seeing was not a scientist but a poet. In the 2nd century of the Common Era, a Syrian satirist named Lucian of Samosata wrote a story called True History, in which a ship sailing beyond the Pillars of Hercules is caught by a waterspout and hurled to the moon. Lucian's lunar explorers discovered a world at war, populated by strange creatures riding 3-headed vultures and fighting battles across terrain no earthly eye had witnessed. The story was fantasy, meant to mock the travel narratives of his day, but embedded within its absurdity was a serious question that would echo through the centuries. What exists on the parts of the moon we cannot see? For most of human history, the question remained purely philosophical. The moon rotates on its axis at precisely the rate required to keep one hemisphere perpetually facing Earth, a phenomenon called synchronous rotation that arises naturally from gravitational interaction between any planet and its close satellite. The Earth's gravity creates a slight bulge in the moon's shape, and over millions of years this bulge acts as a brake on lunar rotation, slowing it until the same face always points toward the gravitational source. Every moon in the solar system that orbits close to its parent planet eventually falls into this locked configuration. The mathematical inevitability of tidal locking meant that no telescope, no matter how powerful, could ever reveal the far side. The limitation was not technological but orbital. The moon simply refuses to turn around. This refusal created a unique situation in the history of exploration. For every other destination humanity has sought to understand, improvements in observation technology eventually rendered physical travel unnecessary for basic reconnaissance. Better telescopes revealed the moons of Jupiter, the rings of Saturn, the polar caps of Mars, the phases of Venus. But the moon's far side remained utterly invisible regardless of how sophisticated Earth-based instruments became. The most advanced observatory in the world, pointed at the moon with perfect tracking and unlimited observing time, would never see a single crater, a single mountain, a single feature of any kind from the hidden hemisphere. The only way to know what lay there was to go there. This made the far side the last truly unknown territory within easy reach of Earth. Not unknown in the sense that Antarctica was unknown before exploration, a place whose existence was suspected but whose details remained unclear. Unknown in an absolute sense, a surface whose very existence could only be inferred from the mathematics of celestial mechanics. The moon obviously had a far side. It was a sphere, and spheres have surfaces that extend around their entire circumference. But no human eye had ever received a single photon reflected from that surface, and no human mind had ever processed an image of its terrain. The philosophical weight of this invisibility accumulated over centuries. Johannes Kepler, the astronomer who discovered the laws of planetary motion, wrote a story in 1608 about a journey to the moon, though his travellers observed only the familiar near side. Cyrano de Bergerac sent fictional explorers to the moon in 1657, imagining lunar inhabitants and lunar customs without addressing the question of what lay beyond the visible crescent. Jules Verne launched 3 travellers around the moon in 1870, and his novel From the Earth to the Moon included a chapter describing their observations of the hidden hemisphere as they swung around the lunar limb. Verne imagined a far side essentially identical to the near side, covered with the same types of craters and maria that dominated Earth-facing views. He had no evidence for this assumption. No one did. It was simply the most reasonable guess available given the information of his era. The reasonable guess turned out to be spectacularly wrong, but more than 80 years would pass before anyone discovered the error. Between Verne's fiction and the first factual observations, the moon transitioned from romantic destination to strategic objective. The far side's mystery became entangled with the far larger mystery of what lay beyond the Earth's atmosphere at all, and with the question of which nation would prove capable of finding out. The machine that would provide the first answer weighed 278 kilograms and carried a camera system that would be considered primitive by the standards of a modern smartphone. Luna 3, launched by the Soviet Union on October 4, 1959, exactly 2 years after the world-changing flight of Sputnik 1, was not originally designed to photograph the far side. The Soviet space program had suffered through a string of failures attempting to reach the moon, and Luna 3's primary mission was simply to demonstrate that a spacecraft could be placed into a trajectory that would carry it around the moon and back toward Earth. The camera system was almost an afterthought, added because the opportunity existed and because success would provide a propaganda victory of incalculable value. The technical challenges facing Luna 3's engineers appear almost quaint from a modern perspective, but they pushed the absolute limits of 1959 technology. The spacecraft needed to orient itself so that its cameras pointed at the moon during the brief window when the far side would be illuminated by the sun. It needed to photograph the lunar surface using film, because no practical method existed for transmitting electronic images at acceptable resolution over interplanetary distances. It then needed to develop that film automatically in an onboard processing system, scan the developed negatives, convert the optical information to radio signals, and transmit those signals back to Earth from a distance, approaching 500,000 kilometers. The film came from an unexpected source. Soviet engineers had recovered American reconnaissance balloon cameras that had drifted over Soviet territory during atmospheric sampling missions. The film in those cameras proved ideal for the Luna 3 mission, a peculiar recycling of espionage technology into exploration hardware. The automatic developing system used a process similar to Polaroid instant photography, treating the exposed film with chemical reagents that fixed the images in place, without requiring the complex temperature-controlled processes of traditional darkroom development. On October 7, 1959, 40 minutes after Luna 3 swung around the moon's far side at a distance of approximately 600 kilometers, the camera shutters opened. Over the next 40 minutes, the spacecraft photographed 29 frames showing roughly 70% of the far side surface. The resolution was coarse by any standard. Individual features smaller than approximately 30 kilometers were invisible. The images were degraded by spacecraft motion, imperfect film handling, and the limitations of the scanning and transmission system. When the photographs arrived at Soviet receiving stations, they revealed a moon that looked almost nothing like the one humanity had observed for thousands of years. The near side of the moon is dominated by Maria, the vast dark plains that ancient observers interpreted as seas. These basaltic floods cover approximately 31% of the near side's visible surface, creating the familiar pattern of light highlands and dark lowlands that has been mapped and named and wondered about since Galileo first turned his telescope toward the lunar disk. The Maria form the man in the moon, the rabbit in the moon, and all the other cultural images that different civilizations have projected onto the lunar face. They are the moon's most recognizable visual feature. The far side had almost none of them. The Luna 3 images, crude as they were, showed a hemisphere covered almost entirely by bright cratered highlands. Two small mare regions were barely visible, but the overwhelming impression was of a surface battered into uniformity by endless impacts, unrelieved by the smooth dark plains that gave the near side its distinctive appearance. Soviet scientists interpreting the photographs over the following months identified approximately 500 features worthy of naming. They called the small visible mare regions Mare Moscoviense and Mare Marginis, and they named craters after Russian scientists and engineers and political figures in a rush to claim nomenclature rights over territory that no one would visit for decades. The asymmetry visible in those first photographs created an immediate scientific puzzle. The near side and far side of the moon are made of the same material. They formed at the same time from the same primordial debris, and they have been exposed to the same bombardment of asteroids and comets over billions of years. There is no obvious reason why one hemisphere should be covered with mare basalts, and the other should not. Yet the difference was unmistakable, recorded in 17 grainy photographs that circled the globe and appeared on the front pages of newspapers from Moscow to New York. The Luna 3 mission established a pattern that would persist for the next decade. Soviet spacecraft continued probing lunar space, achieving additional firsts that included the first soft landing on the moon with Luna 9 in 1966 and the first lunar orbit with Luna 10 the same year. American spacecraft followed, with the Ranger series providing close-up photographs of the lunar surface and the Surveyor series achieving soft landings that returned high-quality surface images. But none of these missions provided significantly better views of the far side. They focused on the near side because that was where future human landings would occur, and the far side remained defined by the Luna 3 photographs, supplemented only by glimpses from the lunar limb regions visible from Earth during favourable librations. The first truly detailed mapping of the far side came from an unexpected source. In 1966 and 1967, 5 American lunar orbiter spacecraft circled the moon photographing potential landing sites for the Apollo program. Their primary mission was to survey near-side locations, but their orbital mechanics carried them around the far side repeatedly, and their cameras recorded thousands of images of terrain no human would set foot on for decades. The lunar orbiter photographs revealed the far side in unprecedented detail, showing individual craters a few hundred meters across and geological features that would occupy researchers for years. They confirmed what Luna 3 had suggested. The far side was a different world. The lunar orbiter data allowed the first serious attempts to measure the far side's topography and to understand the physical basis of the near side-far side asymmetry. Scientists discovered that the far side's crust is significantly thicker than the near side's, averaging approximately 12 kilometers deeper. This thickness difference helps explain the absence of Maria. Volcanic magma rising from the lunar interior would have had to travel through a substantially greater thickness of solid rock to reach the far side surface than to reach the near side surface. In many cases, the magma would have simply stopped, trapped beneath the crust, never flooding the surface with the basaltic lava that created the Mare Plains visible from Earth. But the crustal thickness difference itself demanded explanation. Why would one hemisphere of the Moon develop a crust 12 kilometers thicker than the other? The two hemispheres formed from the same molten magma ocean. They cooled under the same thermal conditions. They should, by any simple reasoning, have ended up with essentially identical crustal structures. The most widely accepted explanation involves the Earth itself. When the Moon formed, it was much closer to Earth than it is today, and the Earth was much hotter, still radiating the energy of its recent formation. This heat preferentially warmed the near side of the Moon, the hemisphere perpetually facing Earth, keeping it warmer than the far side. The temperature difference affected how minerals crystallized as the lunar magma ocean cooled. Certain minerals that form the main components of the lunar highlands preferentially solidified on the cooler far side, building up a thicker crustal layer over millions of years of slow crystallization. By the time the magma ocean fully solidified, the far side had accumulated a crustal blanket substantially thicker than the near side. This explanation links the far side's appearance directly to the Moon's formation and to its ancient relationship with Earth. The far side looks different because it has always been different from the very beginning of lunar history. The mare-free surface visible in the Luna 3 photographs and the lunar orbiter images is not a random geological quirk, but a direct record of conditions that existed when the Moon was young, when the Earth was still glowing with primordial heat, when the entire lunar surface was a sea of molten rock slowly separating into crust and mantle and core. The Apollo missions brought human eyes to lunar space for the first time, but only the three circumlunar missions, Apollo 8, Apollo 10 and Apollo 13, provided direct human observations of the far side. The 6 successful landing missions all touched down on the near side, limited by the requirement for direct radio communication with Earth and by the concentrations of relatively flat mare terrain that provided safe landing zones. The astronauts who walked on the Moon never walked on the far side. They never saw a far side crater from ground level or collected a far side rock sample with their own hands. What they did see from orbit was extraordinary. The Apollo 8 astronauts, the first humans to leave low Earth orbit, circled the Moon 10 times on Christmas Eve 1968. Each orbit took them behind the Moon for approximately 45 minutes, cutting off all contact with Earth and leaving them utterly alone, farther from any other human being than anyone had ever been. Frank Borman, Jim Lovell, and Bill Anders looked down at a battered surface that seemed to stretch to infinity in all directions, unmarked by the familiar dark patches they could see on the near side, cratered and recratered until individual impacts blended into a fractal chaos of overlapping circles. Their observations confirmed what the orbital photographs had shown, but they added something no photograph could capture: scale. The far side craters visible from orbit were enormous, some of them large enough to swallow American states, and they extended without interruption across the entire visible hemisphere. The astronauts described the far side as resembling a beach covered with footprints, where every step left an impression and no area remained unmarked. They photographed particular features and noted colours and textures that photographs barely captured. They became, for 45 minutes at a time, the only conscious beings in the universe with direct perception of the lunar far side. Apollo 8's far side observations were limited by time and equipment. The mission's primary purpose was to test lunar orbital operations, not to conduct extensive surface photography. Later circumlunar missions improved on this foundation, with Apollo 10 providing reconnaissance for the first landing, and Apollo 13 achieving an unplanned but close far-side approach during its emergency return trajectory. By the end of the Apollo program, NASA possessed thousands of photographs of far-side terrain, along with orbital measurements of surface composition and gravity anomalies that suggested complex subsurface structures invisible to cameras. But the Apollo era ended in December 1972, and no human has approached the moon since. 52 years have passed. The astronauts who saw the far side firsthand are aging, some already gone, and the youngest of them was born before the start of the Mercury program. The memories of what the far side looked like from a spacecraft window exist now only in aging minds and archived photographs, in interview transcripts and mission reports, in the fading records of an era that seems increasingly distant. Robotic exploration continued. Soviet lunar missions returned surface samples and deployed rovers on the near side through the mid-1970s. American interest shifted to other destinations, but other nations began their own lunar programs. Japan's Titan spacecraft entered lunar orbit in 1991, beginning a new phase of multinational lunar exploration. The European Space Agency's SMART 1 orbited the Moon from 2004 to 2006, mapping surface composition with instruments far more sophisticated than anything Apollo carried. India's Chandrayaan-1 entered lunar orbit in 2008 and made a discovery of profound importance, detecting the spectral signature of water molecules in permanently shadowed regions near the lunar poles. But the mission that most transformed scientific understanding of the far side launched from Cape Canaveral on June 18, 2009. The Lunar Reconnaissance Orbiter entered lunar orbit 12 days later and has remained there ever since, circling the Moon every 2 hours and returning more data about the lunar surface than all previous missions combined. LRO's camera system can resolve features smaller than a meter across, revealing individual boulders and fresh impact craters in the tracks left by Soviet rovers in the 1970s. Its altimeter has measured the precise elevation of hundreds of millions of points on the lunar surface, building the most detailed topographic map of any world beyond Earth. The LRO data transformed the far side from a region of general features into a landscape of specific places. Individual craters acquired measured depths and documented rim heights. Mountain ranges received accurate elevation profiles. The vast South Pole Aitken Basin, barely visible as a vague dark region in the Lunar 3 photographs, emerged as a feature of staggering dimensions, 2,500 kilometers across and more than 8 kilometers deep, one of the largest impact structures in the known solar system. The South Pole Aitken Basin dominates the southern far side like an ancient wound that never healed. The impact that created it occurred approximately 4.3 billion years ago, during the earliest period of intense solar system bombardment, when leftover debris from planetary formations swept through the inner solar system in quantities that would seem apocalyptic by modern standards. The impactor was probably an asteroid roughly 200 kilometers in diameter, striking the lunar surface at a velocity of approximately 15 kilometers per second. The energy released exceeded the total energy output of the Sun over several days, compressed into a few seconds of violence that excavated material from dozens of kilometers below the surface and threw it across hundreds of thousands of kilometers of surrounding terrain. The basin's floor lies so far below the original surface level that it exposes materials from deep within the lunar crust, possibly from the upper mantle itself. Spectral measurements from orbit have detected unusual mineral compositions within the basin, including elevated concentrations of iron and magnesium that suggest mantle-derived rocks lie exposed on the surface. If true, these rocks represent the deepest natural excavation on the Moon, providing direct access to materials that elsewhere lie buried beneath kilometers of overlying crust. This is the terrain Artemis II will observe during its far-side transit. The crew will pass over the northern portions of the basin, looking down at impact-sculpted landscapes that have remained essentially unchanged since the Hadean eon of Earth's history. They will photograph crater walls that record the angles and velocities of ancient impacts. They will observe colour variations that suggest compositional boundaries between different geological units. They will see with their own eyes a surface that only 27 humans have ever seen directly, and that no living human has seen in more than 50 years. The scientific value of their observations extends beyond simple photography. human vision possesses capabilities that robotic instruments struggle to replicate, including the ability to identify unexpected features, to track subtle colour variations across irregular surfaces, and to integrate multiple visual cues into coherent geological interpretations. The Apollo astronauts repeatedly noticed features that ground-based analysis of their photographs later confirmed but had not predicted. Human observers see differently than cameras, not better in any technical sense, but with a pattern recognition capacity shaped by millions of years of evolution for exactly this purpose, scanning terrain and identifying the significant within the overwhelming. The 4 Artemis II astronauts have spent months training their eyes for geological observation. They have studied lunar maps until the major far side features are as familiar to them as the geography of their home countries. They have practiced recognizing rock types and identifying impact structures in terrestrial analog sites. They have prepared themselves to become the most educated human observers ever to view the far side, capable of extracting maximum scientific value from the brief window when the hidden hemisphere passes beneath their spacecraft. Their observations will address questions that have accumulated since the Luna 3 photographs first revealed the far side asymmetry. Why are there so few Maria? Is the crustal thickness explanation sufficient, or do additional factors contribute? What is the true composition of the South Pole Aitken Basin floor? Does mantle material actually lie exposed, accessible for future sample collection? How do far-side craters differ in preservation state from near-side craters of similar age? Does the difference in resurfacing history, with the far side lacking the volcanic flooding that buried many near-side craters, provide a clearer record of the bombardment chronology that shaped the early solar system? These questions matter beyond lunar science. The Moon is the most accessible archive of conditions that existed when the Earth was young, when life may have been beginning in the primordial oceans, when the entire inner solar system was still settling into its current configuration. The far side's surface, less modified by volcanic activity than the near side, preserves this ancient record more completely than any other accessible location. Understanding the far side means understanding the environment in which terrestrial life originated. The bombardment that repeatedly sterilized early planetary surfaces, the thermal and chemical conditions that eventually permitted stable oceans and atmospheric accumulation on the young Earth. The scientific community waiting for Artemis II data includes researchers from dozens of countries and hundreds of institutions. They have prepared observational priorities and developed analysis protocols. They have identified specific features that crew observations might clarify. They have anticipated questions that high-resolution human observation might answer. The far side has been studied from orbit by instruments of steadily increasing sophistication for 65 years, but the questions keep multiplying because each answered question reveals new complexities that demand further investigation. Some of these complexities emerge from the most recent far-side surface mission, China's Chang'e 4 lander, which touched down within the von Karman crater on January 3, 2019. The landing site lies within the South Pole Aitken Basin, providing the first direct analysis of basin floor material. The Yutu-2 rover that accompanied the lander has traversed more than 1 kilometre of far-side terrain, analysing rock compositions and measuring subsurface structures. Its findings have been surprising. The mineral compositions detected do not match the simple mantle exposure that orbital observation suggested. Instead, the rocks appear to be mixtures of various materials, possibly excavated from different depths by subsequent impacts, and distributed across the basin floor in complex patterns that reflect billions of years of surface evolution. These findings do not resolve the mysteries of the far side, they deepen them. The South Pole Aitken Basin is not a simple window into the lunar interior, but a complex geological environment, whose history involves multiple impact events, possible volcanic modification, and redistribution of surface materials over timescales that dwarf the entire history of life on Earth. Understanding what Yutu-2 has found requires understanding processes that operated before the first cells appeared in Earth's oceans, before the atmosphere contained oxygen, before anything we would recognize as life had any prospect of existence. Artemis II will pass over this landscape from a distance of approximately 100 kilometers, close enough for detailed observation but too high for surface sampling. The crew will photograph the Chang'e 4 landing site, documenting the rover's track and the condition of the surface installation. They will observe the von Karman crater walls and floor, comparing their direct visual impressions with the robotic data that has accumulated over the past 6 years. They will see, in a way that no instrument can replicate, the relationship between local features and the larger basin structure that contains them. The Farside transit will last approximately 45 minutes, similar to the duration experienced by the Apollo 8 crew on their historic first circumnavigation. During this period, the Orion spacecraft will be completely cut off from Earth, unable to receive commands or transmit data, dependent entirely on its onboard systems and the skill of its crew. The isolation is not merely technical, but psychological. The astronauts will know that no human voice can reach them, that no assistance can arrive, that they are farther from help than any human being except their 3 crewmates. This isolation has affected every astronaut who experienced it. The Apollo crews described the Farside passage as simultaneously beautiful and unnerving, a period of awareness that the universe is vastly larger and more indifferent than everyday experience suggests. When Artemis II emerges from behind the moon and radio contact resumes, the crew will transmit their observations to an audience that extends far beyond the scientific community. The mission is designed to inspire as well as investigate, to remind a species increasingly focused on terrestrial concerns that the universe remains vast and unexplored and full of mysteries that await anyone with the courage to seek them. The Farside photographs will appear on screens around the world within minutes of transmission, the first new human observations of the hidden hemisphere in half a century, fresh views of an ancient surface that has waited in darkness for someone to return. The scientific questions are complex. The human questions are simpler. What does it look like? What does it feel like to be there? What remains to be discovered on a surface that has been photographed for 65 years, but visited by humans for 0 hours? These are the questions Artemis II will begin to answer, not with equations or spectral analyses, but with the direct testimony of human beings who have seen something extraordinary, and who return to describe it. The far side of the moon holds secrets that instruments alone cannot fully reveal. This is not mysticism or sentiment. It is a recognition that human perception operates differently from mechanical detection, that the trained eye integrated with a questioning mind notices patterns and anomalies that automated systems are not programmed to seek. The Apollo astronauts demonstrated this repeatedly. They observed features that orbital photography had missed, asked questions that revised scientific understanding, made connections between observations in different locations that revealed processes no one had anticipated. The Artemis II crew carries this same capacity for discovery, enhanced by 50 years of accumulated knowledge about what questions remain unanswered and what observations might resolve them. The mineralogy of the Farside Highlands presents one of these persistent questions. Spectroscopic mapping from orbit has revealed that the Farside crust differs significantly from the near side in its chemical composition. The Farside appears to be enriched in certain elements and depleted in others, patterns that speak to how the original lunar crust formed from the crystallizing magma ocean, and how subsequent impacts and volcanic activity modified that primordial surface. But spectroscopy from orbit penetrates only the uppermost millimeters of the surface, and those millimeters have been gardened and mixed by billions of years of micrometeorite bombardment. The true composition of the underlying rock remains uncertain, extrapolated from surface measurements that may or may not represent the deeper material. Visual observation from the Orion spacecraft will not resolve this uncertainty directly. The crew cannot collect samples or deploy instruments, but they can observe the relationship between surface color and topography in ways that orbital cameras cannot replicate. Fresh impact craters excavate material from depth, exposing rock that has not been subjected to the full history of space weathering. These bright rayed craters stand out against the darker surrounding terrain, their ejecta blankets revealing the color of subsurface material. An experienced observer can assess the depth and freshness of these exposures, noting which craters penetrate deeply enough to sample the underlying bedrock, and which merely redistribute already weathered surface material. The crew will also observe shadow patterns that reveal subtle topographic features, invisible in direct sunlight. The far side passage will occur at a solar angle that creates long shadows in some regions and eliminates them in others, depending on local time relative to the terminator. The astronauts can choose where to direct their attention, focusing on areas where the lighting geometry reveals maximum topographic detail. This selective observation is something orbital photography cannot achieve effectively. Satellites pass on predetermined paths at times determined by orbital mechanics, capturing whatever lighting conditions happen to exist. The Artemis II crew can wait for optimal moments, adjust their viewing angle, and concentrate their attention on features that appear most scientifically interesting. The far side highlands contain numerous ghost craters, ancient impact structures whose rims have been degraded by billions of years of subsequent bombardment until they appear as faint circular patterns, barely distinguishable from the surrounding terrain. These ghost craters mark the locations of some of the oldest preserved impacts on the Moon, events that occurred during the late heavy bombardment approximately 4 billion years ago or earlier. They are difficult to identify in orbital photography because their topographic expression is so subdued, but under certain lighting conditions their circular outlines become visible to a human observer trained to recognize them. Mapping these ghost craters matters because their distribution and size frequency reveal information about the impactor population in the early solar system. Were the objects that created these craters predominantly asteroids displaced from the main belt, or did they include significant numbers of comets from the outer solar system? The size distribution of craters can distinguish between these populations, but accurate size measurements require identifying craters that have been partially erased by time. Human observers excel at this kind of pattern recognition, at distinguishing the subtle circular hint of an ancient rim from the random irregularities of unrelated terrain. The far-side transit also offers observational opportunities that have nothing to do with the surface itself. The Moon casts a shadow in space, a cone of darkness extending away from the Sun, where the solar wind cannot penetrate, and where conditions differ dramatically from the exposed surface. This shadow, called the lunar wake, extends behind the Moon for distances that vary with solar wind conditions, but typically reach several lunar radii into space. Artemis II will pass through portions of this wake during its trajectory, exposing the spacecraft to an environment where charged particle bombardment temporarily decreases. Scientists have studied the lunar wake extensively using robotic spacecraft, but no crewed vehicle has carried instruments designed to characterize it in detail since the Apollo era. The Orion spacecraft carries radiation monitoring equipment intended primarily to assess crew exposure levels, but this same equipment will record the radiation environment throughout the mission profile, including the passage through the lunar wake. These measurements will add to the database of observations characterizing the space environment that future long-duration missions will encounter. The radiation environment near the Moon represents one of the most significant challenges for sustained human presence beyond low Earth orbit. The International Space Station orbits within Earth's magnetosphere, protected from the worst solar and cosmic radiation by the same magnetic field that creates the aurora. The Moon has no such protection. Solar energetic particles and galactic cosmic rays strike the lunar surface and the space around it, with essentially no attenuation. Astronauts working on the lunar surface will accumulate radiation doses far higher than those experienced in low Earth orbit, and understanding exactly how high requires measurements at the Moon itself. Artemis Theka will provide some of these measurements, not from the surface but from lunar orbital space. The radiation environment at the surface differs from that in orbit, because the Moon itself blocks half the sky, providing a solid shield in one direction. From orbit, radiation arrives from all directions, and the doses accumulated there establish baseline values for the unshielded environment. Future surface missions will compare their measurements to these orbital baselines, distinguishing the effects of surface proximity from the effects of variations in solar activity. The far side passage adds another dimension to this radiation characterization. Radio silence during far side transit is complete. No signals from Earth reach the spacecraft, and no signals from the spacecraft reach Earth. But the far side also partially shields the spacecraft from certain radiation sources. Earth itself is a weak source of radio emissions and charged particles, products of the planet's magnetosphere interacting with the solar wind. These Earth origin particles cannot reach the far side, blocked by the Moon's bulk, just as radio signals are blocked. The radiation environment on the far side is therefore slightly different from that on the near side, a difference that may matter for future communications infrastructure on the lunar surface. Scientists have proposed placing radio telescopes on the lunar far side, taking advantage of the Moon's bulk to shield against Earth origin radio interference. Such telescopes could observe frequencies that are impossible to detect from Earth's surface, or even from Earth orbit, opening new windows into the radio universe. But establishing far-side installations requires understanding the radiation environment there, not just for the instruments themselves, but for any human workers who might install or maintain them. Artemis II carries instruments that will contribute to this characterization, filling gaps in the knowledge base that will inform decisions about where and how to establish permanent far-side presence. The trajectory of Artemis II carries it not only around the Moon, but also to distances from Earth that exceed those achieved by any human mission since Apollo 17. At its farthest point, Orion will be approximately 450,000 kilometers from Earth, setting a new record for the greatest distance travelled by humans from their home planet. This milestone is not merely symbolic. It places the spacecraft in regions of space where the influence of Earth has faded to near insignificance, and where the gravitational and radiation environment represents deep space conditions. The crew will experience this distance not as a number, but as a physical reality. Radio signals take approximately 3 seconds for a round trip at maximum distance, creating a noticeable lag in communications. The Earth will appear small enough to cover with an extended thumb, a perspective that Apollo astronauts described as transformative. They could no longer pretend that Earth was the centre of everything, that human concerns were cosmically significant, that the universe existed as a backdrop for human drama. The fragility and isolation of the home planet became viscerally apparent, understanding that influenced the environmental consciousness of the following decades. Artemis II crew members will experience this same perspective shift, the first humans in 50 years to see Earth as a small, isolated world in an enormous universe. They will photograph their home planet from maximum distance, creating images that will join the iconic Apollo photographs in the cultural memory of the species. But they will also take measurements that the Apollo missions could not, characterizing the space environment at distances that matter for future deep space missions. The gravitational influence of the Moon extends far beyond the lunar surface, creating regions where orbital dynamics become complex and where spacecraft can achieve stable or semi-stable positions with minimal fuel expenditure. These Lagrange points and their associated halo orbits will be crucial for future lunar operations. A space station positioned at the L2 point behind the Moon could serve as a communications relay for far-side surface operations, maintaining constant contact with Earth while providing line of sight to installations on the hidden hemisphere. Artemis II will not visit the L2 point, but its trajectory will carry it through regions where the gravitational influences of Earth and Moon combine in complex ways. The navigation data gathered during this passage will refine understanding of the gravitational environment, improving the accuracy of future trajectory calculations. Every deep space mission contributes to this accumulated knowledge, and Artemis II will be the first crewed mission in decades to operate in the Earth-Moon gravitational system beyond low Earth orbit. The far-side transit itself represents approximately 2% of the total mission duration. 10 days of total flight time condense into 45 minutes of complete isolation, less than an hour during which the crew passes over terrain that only orbital cameras and a single surface rover have observed. The brevity of this passage might suggest that the far side represents a minor element of the mission's scientific return. This impression would be mistaken. The far side observation period is brief but intensely focused, a window of opportunity that concentrates attention and maximizes the value of every passing second. The crew will have trained extensively for this period, memorizing the locations of key features and the observations that surface scientists most urgently want. They will know which craters to photograph, which formations to examine, which questions their observations might help answer. This preparation transforms a brief passage into a systematic survey, a directed investigation that extracts maximum information from limited time. Mission controllers will have uploaded detailed observation plans before radio contact is lost. These plans will specify targets in order of priority, ensuring that the most important observations are completed first in case unexpected events consume the remaining time. The crew will execute these plans while remaining alert for unexpected features that deserve documentation, balancing the predetermined priorities with the exploratory spirit that makes human observation valuable. When radio contact resumes after the far side passage, the crew will begin transmitting their observations immediately. Preliminary verbal descriptions will precede the images, giving scientists on Earth their first indication of what the astronauts observed. These descriptions matter more than might be apparent. Trained observers notice things that cameras do not capture, relationships between features that require human judgment to perceive. the crew's verbal reports will guide the analysis of the photographic data, directing attention to the features that seemed most significant from the spacecraft. The photographs themselves will require time to transmit fully. High-resolution imagery from the far side will flow to Earth over the hours following the passage, arriving in order of scientific priority. Mission controllers and science teams will analyze these images in real time, identifying features that warrant follow-up observation during the return trajectory. Artemis II will pass over the far side again on its way back to Earth, providing a second opportunity for observation from a different angle and under different lighting conditions. This second passage will be briefer than the first, the spacecraft moving faster as it falls back toward Earth's gravitational embrace. But the observations from this second pass will complement those from the first, revealing features that were shadowed before or confirming details that appeared ambiguous in single images. Stereoscopic analysis of images from different angles will reveal topographic information that single-angle photography cannot provide, and the crew's observations during both passages will create a more complete picture than either passage alone could achieve. The accumulated observations from Artemis II will feed into planning for future missions. Artemis III will land astronauts on the lunar surface, though the planned landing site is in the South Polar region rather than the far side. The polar regions present their own scientific opportunities, including the possibility of water ice in permanently shadowed craters, but the far side will eventually receive human visitors as well. The observations from Artemis Test will help select those future landing sites, identifying regions that balance scientific interest with operational safety. Landing on the far side presents challenges that near-side landings do not. Communication with Earth is impossible without relay satellites, and the terrain is generally rougher than the Mare plains where Apollo landed. But the scientific rewards of far-side surface access are proportionally greater. Direct sampling of South Pole Aitken basin floor material could answer questions about lunar interior composition that decades of orbital observation have left unresolved. Seismic measurements on the far side could characterize the lunar interior structure from a perspective that complements near-side measurements. The far side is not merely interesting, it is essential for understanding the Moon as a complete world rather than as a half-observed enigma. The preparation for such future missions begins with Artemis II. Every observation the crew makes, every measurement the spacecraft records, every moment of far-side passage contributes to the knowledge base that will inform future exploration. The mission is a reconnaissance, a systematic gathering of information that will enable increasingly ambitious endeavours. The crew members are not merely passengers on a ceremonial voyage. They are advanced scouts for a program that intends to establish permanent human presence beyond Earth. This context gives weight to observations that might otherwise seem routine. When Commander Reed Wiseman photographs a far-side crater, he's not taking a tourist snapshot. He is documenting terrain that future explorers may traverse, noting features that might present obstacles or opportunities, creating visual records that will appear in planning documents and training materials for decades to come. When pilot Victor Glover observes the relationship between highland terrain and mare-filled basins, he is testing whether human perception can add information to orbital data, whether the investment in crude observation pays returns that robotic missions cannot match. The answer to this question will influence the entire future of human space exploration. If Artemis Test demonstrates that human observers contribute unique and irreplaceable value, then the argument for human presence beyond Earth strengthens considerably. If the observations prove no better than what automated cameras could achieve, then the calculus shifts toward robotic exploration, with human presence reserved for tasks that genuinely require it. The crew is not merely observing the Moon. They are demonstrating the value of human observation itself, proving or disproving a hypothesis about whether people belong in space. The far side serves as an ideal test case for this demonstration. It is unfamiliar enough that orbital data has not exhausted its mysteries. It is close enough that detailed observation is possible. It is sufficiently complex that experienced human judgment might notice patterns that automated analysis would miss. If human observation adds value anywhere in the lunar environment, it should add value on the far side where so much remains unknown and where the unexpected may lurk in every crater. The crew understands this responsibility. They have trained not merely to execute predefined observation plans, but to think as scientists, to notice anomalies, to ask questions that the plans did not anticipate. This scientific mindset distinguishes exploration from tourism, transforming a spectacular journey into a productive investigation. The views will be magnificent regardless of what the crew does. The scientific return depends on how well they observe, how clearly they think, and how effectively they communicate what they notice. The communication challenge extends beyond the technical difficulties of radio relay. It involves translating visual experience into words and images that convey meaning to people who cannot see what the crew sees. This translation is harder than it appears. Photographs capture light but not context. Words describe features but not the relationships between them. The astronauts must learn to be observers and interpreters simultaneously, seeing with scientific precision and describing with sufficient clarity that scientists on Earth can reconstruct the observation from the description. This dual role has precedence in the history of exploration. The naturalists who accompanied sailing expeditions in the 18th and 19th centuries faced similar challenges. They observed unfamiliar landscapes and creatures, documented their observations in journals and sketches, and returned to communicate their findings to colleagues who had not made the journey. Their success depended not only on what they observed, but on how effectively they conveyed their observations to others. The same skills matter for space exploration, though the medium has changed from sketches to digital photography, and from handwritten journals to real-time voice communication. The far side passage will test these skills under time pressure. 45 minutes allows no leisurely contemplation, no extended analysis, no second chances for observations missed. The crew must observe rapidly, prioritize correctly, and document efficiently, all while managing the spacecraft and monitoring systems that could fail without warning. This intensity concentrates the mind in ways that leisurely observation cannot, and the observations produced under such pressure often prove more valuable than those made at leisure. Necessity forces clarity, and the need to observe quickly forces attention to what matters most. The return to radio contact after far-side passage marks a transition in the mission. The outbound journey culminates in the lunar flyby. The return journey carries the crew back toward Earth. The mission objectives largely complete, but the spacecraft still far from home. The psychological dynamics of return differ from those of approach. The excitement of approaching an unknown destination yields to the anticipation of returning to a familiar one. The urgency of exploration yields to the patience of endurance. The crew must remain alert through days of travel during which nothing dramatic happens, maintaining vigilance despite the absence of immediate challenges. This shift from exploration to endurance reveals something fundamental about human spaceflight that the public rarely considers. The dramatic moments of a mission, the launch, the lunar flyby, the splashdown, occupy mere hours of a journey that spans days. The intervening time tests different qualities than those required for the dramatic peaks. Patience matters more than courage. Consistency matters more than brilliance. The ability to maintain focus through monotony proves as essential as the ability to respond quickly under pressure. The crew of Artemis II is trained for both conditions, understanding that the mission succeeds or fails not in the spectacular moments, but in the aggregate of thousands of ordinary ones. The return trajectory from the Moon follows a path shaped by the same gravitational forces that guided the outbound journey. But the crew experiences it differently. The Moon shrinks behind them as the Earth grows ahead. The psychological weight of this visual transformation affects astronauts in ways that surprised the Apollo crews. Several reported feeling a sense of loss as the lunar surface receded, as if something precious was being taken from them. They'd travelled farther than any humans in history to reach that barren world, and now they were leaving it behind, possibly forever. The intensity of this feeling surprised men who thought of themselves as test pilots rather than poets, pragmatists rather than romantics. But the Moon evokes responses that transcend professional training, and the experience of departing from it stirs emotions that no amount of preparation fully anticipates. For the Artemis II crew, this departure carries additional weight because they know they will not land. They have come closer to the lunar surface than any humans in 5 decades, close enough to see individual boulders and the tracks that lunar rovers might someday leave, yet they will not set foot on the regolith that seems almost within reach. This near miss creates a peculiar psychological tension. The mission accomplishes everything it was designed to accomplish, yet the proximity of something more, of actual landing, of footprints in the dust, makes the accomplishment feel incomplete. The crew understands intellectually that their mission was never intended to include landing, that Artemis II serves as a necessary step toward Artemis III, where landing will occur. But intellectual understanding does not fully resolve emotional tension, and the experience of turning away from the moon after coming so close generates feelings that future astronauts will recognize in their own missions. The return journey also provides time for the crew to process what they have observed. The 45 minutes of far-side passage passed too quickly for thorough analysis. The observations were necessarily impressionistic, capturing initial reactions rather than considered conclusions. The days of return travel allowed deeper reflection, enabling the crew to compare what they observed with what they expected, to identify discrepancies that merit attention, to formulate hypotheses that scientists on Earth can investigate further. This processing time transforms raw observation into structured knowledge, converting the crew's visual experiences into information that the scientific community can evaluate and build upon. The communication during return travel differs qualitatively from communication during the lunar approach. The approach communications carried urgency, the need to coordinate observations, to capture fleeting opportunities, to document phenomena that would soon pass out of view. The return communications allow more leisurely discussion, enabling the crew to describe their experiences in greater detail and to answer questions from scientists who have had time to review preliminary data. This extended dialogue often produces insights that neither the crew nor the ground controllers would have reached independently. The crew saw things that the scientists did not, while the scientists know things that inform interpretation of what the crew saw. The synthesis of these perspectives generates understanding that exceeds what either group possesses alone. The technical monitoring during return requires sustained attention, despite the reduced drama. The spacecraft systems that performed flawlessly during the outbound journey must continue performing through the return. The thermal protection systems that will shield the capsule during re-entry need verification. The navigation calculations that will guide the spacecraft to precise splashdown coordinates need refinement. The communication systems that will track the capsule through the plasma blackout of re-entry need testing. Each of these systems involves complex engineering that could fail in ways that are not immediately apparent, and the crew must monitor for subtle anomalies that might indicate impending problems. This vigilance cannot relax simply because the most exciting portion of the mission has concluded. The approach to Earth re-entry represents the final major challenge of the mission, and in many ways the most dangerous. The spacecraft returns from the Moon travelling approximately 25,000 miles per hour, significantly faster than spacecraft returning from low Earth orbit. This additional velocity means additional heat during re-entry, temperatures that approach those at the surface of the Sun concentrated on a heat shield that must perform perfectly, or not at all. The crew has no ability to repair the heat shield if problems develop during the mission. They must trust the engineering that designed it, the manufacturing that built it, and the inspections that verified it before launch. This trust is not blind faith, but informed confidence based on extensive testing. Yet no test perfectly replicates the conditions of actual re-entry, and the crew enters the atmosphere knowing that they are betting their lives on systems they cannot fully verify. The re-entry corridor for a lunar return is narrower than for orbital re-entry, requiring more precise navigation. If the spacecraft enters the atmosphere too steeply, the deceleration forces could exceed what the crew can survive, and the heat shield could face temperatures beyond its design limits. If the spacecraft enters too shallowly, it could skip off the atmosphere like a stone skipping across water, departing on a trajectory that might take it thousands of miles from the intended recovery zone or even back into space. The window between these extremes spans only a few degrees, and the navigation must place the spacecraft within this window with high precision, despite the uncertainties accumulated over 10 days of flight. The Orion spacecraft addresses this challenge through a technique called skip re-entry, in which the capsule dips into the atmosphere, uses the atmospheric drag to slow down and generate lift, then rises back out of the atmosphere before re-entering for final descent. This technique extends the range of accessible splashdown points and reduces peak heating by spreading the total heat load across 2 atmospheric passages rather than 1. The skip re-entry requires sophisticated guidance, and Artemis II will demonstrate this technique for the first time with humans aboard. The success of this demonstration opens possibilities for future missions, while failure would force reconsideration of the re-entry approach for all subsequent Artemis flights. The crew experiences the skip re-entry, as a sequence of acceleration forces punctuated by brief periods of relative calm. The initial atmospheric contact produces forces that press the crew into their seats, forces that build gradually as the atmosphere thickens, then diminish as the capsule climbs back toward the vacuum of space. The second entry produces similar forces but with the addition of heat that the crew can sense even through the protection of the heat shield and spacecraft structure. The windows glow orange with ionized plasma, and for several minutes communication with Earth becomes impossible as the plasma sheath blocks radio signals. This communication blackout creates perhaps the most tense period of the mission for the ground controllers, who can only wait and hope that the spacecraft emerges intact on the other side. The plasma sheath that blocks communication results from air molecules being torn apart by the extreme heat of re-entry. The violence of this process, the dissociation of molecules into ions and free electrons, creates a boundary layer around the spacecraft that reflects radio waves rather than transmitting them. The crew inside the capsule can see the plasma glowing outside their windows, can feel the spacecraft shuddering as it decelerates through thickening atmosphere, can hear the roar of supersonic airflow, but they cannot speak to anyone beyond the boundary of their small craft. They are alone in a way that even the far side radio blackout did not achieve, because at least on the far side the crew knew that communication would resume automatically when the spacecraft moved to where it could see Earth. During re-entry blackout, communication resumes only if the spacecraft survives, and the crew cannot know with certainty that survival will occur until it does. The emergence from blackout produces one of the most anticipated moments of any space mission. The sudden return of telemetry, the first voice transmission from the crew confirming that they are well, the tracking data showing the capsule descending on the expected trajectory, all of these signals carry relief that spreads through mission control and beyond to the millions watching the mission unfold. The crew still faces challenges: the parachute deployment, the splashdown, the recovery by naval forces. But these challenges involve systems that have been tested extensively and that offer redundancy against individual failures. The re-entry itself allows no redundancy. The heat shield either works or it does not. The emergence from blackout confirms that it worked, and the remainder of the descent proceeds with progressively increasing confidence. The parachute sequence for Orion involves multiple stages designed to slow the capsule from supersonic speeds to a gentle splashdown. The drogue parachutes deploy first, stabilizing the capsule and providing initial deceleration. The main parachutes deploy afterward, 3 massive canopies that together span more than 120 feet in diameter. The system is designed to tolerate the failure of one main parachute, allowing safe splashdown even with only 2 functioning canopies, though the impact forces would be higher and the crew would experience a rougher landing. The visual spectacle of the parachute deployment, the bright colours against blue sky, the orderly inflation of the canopies, the gradual descent toward ocean waters creates some of the most iconic imagery of any space mission. The splashdown location is chosen based on weather conditions, naval positioning and trajectory constraints, resulting in a landing zone somewhere in the Pacific Ocean where recovery forces can reach the capsule quickly. The crew remains inside the capsule after splashdown, waiting for divers to arrive and attach flotation devices that ensure the capsule remains stable even in significant waves. The hatch opens to reveal a world that the crew has not experienced for 10 days, air that carries the salt smell of ocean, light that comes from a sun that appears subtly different after days of viewing it without atmospheric filtering, gravity that pulls with a weight that feels unfamiliar after the weightlessness of space travel. The readjustment to Earth conditions begins immediately, though full readaptation takes days or weeks depending on the individual. The medical evaluation that follows splashdown assesses how the crew responded to the 10-day mission, looking for changes that might inform understanding of longer missions and identifying any immediate health concerns that require attention. The relatively short duration of Artemis II limits the physiological changes the crew experiences, but even 10 days in microgravity produces measurable effects on cardiovascular function, bone density, and vestibular adaptation. These effects reverse quickly for most crew members, though the experience of readjusting to gravity proves disorienting in ways that surprise astronauts who thought they had prepared adequately for the transition. The scientific debriefing that follows the medical evaluation allows the crew to share their observations with researchers who have been analysing preliminary data since the mission began. These debriefing sessions often produce insights that neither the crew nor the scientists anticipated, as the combination of direct experience and analytical expertise generates understanding that neither perspective achieves alone. The crew describes phenomena that they noticed but could not explain, while scientists identify the significance of observations that the crew mention casually without recognizing their importance. This collaborative interpretation represents one of the distinctive values of human spaceflight, the ability to engage in nuanced dialogue about observations that automated systems could not conduct. The public communication following the mission extends beyond formal press conferences to include educational outreach, documentary participation, and personal appearances that allow the crew to share their experiences with audiences who could not participate in real time. These communications shape public perception of space exploration, influencing whether the public views the investment as worthwhile and whether future missions receive the support they need to proceed. The crew becomes ambassadors for the program, translating their technical experiences into stories that resonate with people who may never leave Earth, but who can still appreciate the significance of what the mission accomplished. The legacy of Artemis II will depend partly on what the mission achieves technically and partly on how effectively those achievements are communicated to the public. A successful mission that the public neither understands nor values produces less lasting impact than a moderately successful mission that captures public imagination and inspires continued investment in exploration. The crew understands this responsibility, which is why their training includes communication skills, alongside piloting and scientific observation. They must be able to describe what they experienced in terms that matter to people whose daily concerns focus on matters far removed from lunar trajectories and spacecraft systems. The scientific data from the Farside passage will take months or years to analyse fully, but initial findings will emerge quickly as researchers examine the photographs and sensor readings that the crew transmitted during and after the flyby. These preliminary findings will address immediate questions while raising new ones that future missions must investigate. The resolution of some mysteries will reveal additional mysteries that the current data cannot resolve, a pattern that characterizes scientific exploration across all fields and all eras. Each answer generates new questions, and progress consists not in eliminating questions but in asking better ones. The specific mysteries that Artemis II might illuminate span the full range of lunar science, from the composition of crater floors to the structure of the deep interior. The Farside observations contribute to understanding lunar asymmetry, the curious fact that the near side and far side differ dramatically in their geological character. The near side contains large dark regions called maria, basaltic plains formed by ancient lava flows that filled giant impact basins billions of years ago. The far side has almost no maria, instead presenting a surface dominated by highlands and impact craters with relatively little evidence of volcanic flooding. This asymmetry has puzzled scientists since the first spacecraft images revealed it, and multiple hypotheses attempt to explain why volcanic activity concentrated so strongly on the near side. One hypothesis proposes that the asymmetry relates to crustal thickness, with the far side crust being significantly thicker than the near side crust. Thicker crust could have prevented magma from reaching the surface on the far side, while thinner crust allowed volcanic eruptions on the near side. The Grail mission's gravity mapping strongly supports this hypothesis, showing that the far side crust is indeed substantially thicker, but the reason for this thickness difference remains debated. Some models suggest that a large impact early in lunar history removed crustal material from what is now the near side, creating the thickness difference as a consequence of violent collision. Other models propose that processes of crustal formation inherently produced asymmetric thickness, perhaps related to the thermal conditions at the time the crust solidified from the lunar magma ocean. The observations from Artemis II cannot definitively resolve this question, but they might provide constraints that favour some hypotheses over others. Another hypothesis focuses on the distribution of radioactive elements within the Moon, elements whose decay produces heat that could drive volcanic activity. These elements appear to concentrate in a region called the Procellarum creep terrain, which underlies much of the near side and contains elevated levels of potassium, rare earth elements, and phosphorus. The heat generated by radioactive decay in this region could have prolonged volcanic activity on the near side long after the far side cooled and solidified. If this hypothesis is correct, the far side would show evidence of earlier cooling, perhaps expressed in surface features that indicate when volcanic activity ceased. The crew's observations of the far side might reveal such features, though interpretation would require careful analysis and comparison with existing orbital data. The compositional differences between near-side and far-side extend beyond the presence or absence of Maria to include variations in mineral content and surface chemistry. The far-side highlands appear slightly different in composition from the near-side highlands, differences subtle enough that only precise spectroscopic measurements can detect them. These differences might reflect variations in the original magma ocean that covered the early Moon, variations in the subsequent bombardment history, or variations in surface processes that have modified the regolith over billions of years. Each possibility carries implications for understanding not just the Moon but the early Earth-Moon system as a whole, because the Moon preserves a record of conditions that the Earth has long since erased through geological activity. The South Pole Aitken Basin represents perhaps the most significant single feature that Artemis II will observe during its far-side transit, a structure so immense and so ancient that understanding its formation could unlock secrets about the earliest period of solar system history. This basin measures approximately 2,500 kilometres in diameter and reaches depths of more than 8 kilometres below the surrounding terrain, making it one of the largest and deepest impact structures known anywhere in the solar system. The asteroid or comet that created this feature struck the lunar far side approximately 4.3 billion years ago, during the period when the inner solar system experienced intense bombardment from leftover debris of planetary formation. The violence of this impact defies easy comprehension, releasing energy equivalent to billions of nuclear weapons detonating simultaneously, excavating cubic kilometres of crustal material, and flinging it across the lunar surface and into space. Some of this ejected material likely reached Earth, though any terrestrial evidence has long since been erased by plate tectonics and erosion. The basin's significance extends far beyond its impressive dimensions to include its potential for revealing the composition of the lunar interior. The impact that created South Pole Aitken excavated so deeply that it may have penetrated through the crust and into the underlying mantle, exposing material that otherwise remains hidden beneath kilometres of crustal rock. Spectroscopic observations from orbit have detected elevated iron content within the basin, consistent with the hypothesis that mantle material lies exposed on its floor. If this interpretation is correct, the basin provides a natural window into the Moon's interior, allowing study of materials that formed during the earliest stages of lunar differentiation. The crew of Artemis II will pass over this basin during their far-side transit, observing its massive extent and noting variations in surface colour and texture that might indicate compositional differences between regions. Their visual observations will complement decades of orbital measurements, potentially revealing details that automated instruments could not capture. The age of South Pole Aitken Basin places it within a critical period of solar system evolution, the late heavy bombardment that reshaped the surfaces of all inner solar system bodies between approximately 4.1 and 3.8 billion years ago. During this period, gravitational interactions among the giant planets may have destabilized the orbits of countless asteroids and comets, sending them cascading through the inner solar system in a cosmic storm of impacts. The evidence for this bombardment comes primarily from the Moon, where ancient surfaces preserve impact craters dating to this era, craters that have been erased on Earth by geological activity, but remain visible on the geologically dead lunar surface. Understanding the timing and intensity of the late heavy bombardment carries implications for the origin of life on Earth, because the same period that saw devastating impacts also witnessed the emergence of the first living organisms. If impacts were truly as intense as some models suggest, they might have sterilized Earth's surface repeatedly, requiring life to emerge quickly during brief intervals between catastrophic collisions. Alternatively, if the bombardment was less severe than proposed, life might have had longer periods of relative calm in which to develop and diversify. The South Pole Aitken Basin serves as a reference point for understanding this critical epoch, its age and size providing constraints on the impactor population and impact rates during the early solar system. The basin also contains scientific targets of particular interest for future exploration, regions where specific measurements might answer questions that orbital observations cannot address. Among the most intriguing is the basin floor itself, where materials excavated from great depth may lie exposed and accessible for sampling. A future robotic or crewed mission that could collect samples from this region would potentially return pieces of the lunar mantle, materials that have never been available for laboratory study. The analysis of such samples would revolutionize understanding of lunar interior composition, providing direct evidence rather than the indirect inferences currently required. The crew of Artemis II will observe the basin with knowledge that future missions may visit its surface, their observations contributing to the planning and site selection for those subsequent endeavours. The far side of the Moon also presents unique opportunities for astronomical observation, opportunities that arise precisely from the lunar body blocking all radio emissions from Earth. The near side of the Moon experiences continuous exposure to radio transmissions from human civilization, transmissions that have grown exponentially more intense over the past century as communication technologies have proliferated. These signals create a background of radio frequency interference that complicates astronomical observations, particularly observations attempting to detect extremely faint signals from the distant universe. The far side, permanently shielded from Earth by the bulk of the Moon itself, offers the only location within easy reach of Earth where this interference essentially vanishes. The radio quiet of the far side makes it an ideal site for certain types of astronomical observation that cannot be conducted anywhere else. Observations that require sensitivity to signals far weaker than the electromagnetic noise that saturates near-Earth space. Among the most compelling applications for far-side radio astronomy involves observations of the cosmic dark ages, the period between the emission of the cosmic microwave background approximately 380,000 years after the Big Bang, and the formation of the first stars perhaps 100 million years later. During this interval, the universe contained hydrogen gas that had cooled enough to become neutral, gas that emitted faint radio signals at a characteristic wavelength of 21 centimeters. These signals have since been redshifted by cosmic expansion to much longer wavelengths, stretching into frequency bands heavily contaminated by human-generated radio interference. Detecting the pristine signal from the Dark Ages requires observations from a location completely free from this interference, a location that exists in only one easily accessible place in the entire solar system, the far side of the Moon. Future radio telescopes positioned on the far side could potentially detect this signal, opening a window onto an era of cosmic history that remains almost entirely unexplored. The observations would reveal how matter was distributed in the early universe, how the first density variations grew into the structures that would eventually become galaxies, and how the transition from cosmic darkness to the first starlight unfolded across the cosmos. The crew of Artemis II will not deploy radio telescopes on the far side, but their mission contributes to the technological and operational foundations that could make such deployments possible. Every crewed mission beyond low Earth orbit advances understanding of the systems and procedures required for more ambitious operations, reducing the risk and increasing the feasibility of future endeavours. The demonstration that humans can safely travel to lunar distance, operate effectively in deep space, and return home successfully represents an essential precursor to establishing any permanent presence on or around the Moon. The specific observations the crew makes during their far-side transit provide scientific value in their own right, while also supporting the planning for future missions that might establish far-side infrastructure for radio astronomy or other purposes. The far side contains numerous individual features that will draw the attention of the crew as they pass overhead, features whose scientific significance has emerged from decades of orbital observation and analysis. Among these is the crater Tsiolkovsky, named for the Russian rocket pioneer whose mathematical work in the early 20th century laid the theoretical foundations for spaceflight. This crater presents one of the most striking visual features on the entire far side, its dark floor contrasting sharply with the bright surrounding terrain. The darkness of Tsiolkovsky's floor results from basaltic lava flows that flooded the crater interior long after the impact that formed it, one of the few examples of Maria-like volcanic activity on the far side. The presence of this volcanic fill raises questions about why volcanism occurred here when it is so rare elsewhere on the far side, questions that might relate to local crustal thickness, subsurface composition, or thermal conditions that differed from typical far-side environments. The crater's central peak rises from the dark floor, a feature formed during the impact itself when the crater floor rebounded upward, following the initial compression of the collision. The composition of this central peak might differ from the surrounding material, potentially exposing rocks excavated from beneath the surface that could reveal information about the far-side crust at depth. The crater Korolev presents another far-side feature of considerable scientific interest, its floor containing evidence of relatively recent geological activity in the form of volcanic features that appear younger than typical far-side terrain. Named for Sergei Korolev, the chief designer who led the Soviet space program through its greatest achievements, including the launch of Sputnik and the flights of Yuri Gagarin, this crater occupies a position on the far side's northern regions. The volcanic features within Korolev suggest that some volcanic activity persisted on the far side longer than previously thought, challenging simple models that assume far-side volcanism ceased much earlier than near-side volcanism. Understanding the chronology of volcanic activity on the far side requires precise age dating that currently comes only from sample analysis, making these regions high-priority targets for future sample return missions. The observations from Artemis II cannot determine ages, but can characterize surface features in ways that support planning for those future missions, identifying regions where sample collection might prove most scientifically productive. The far side also preserves evidence of more recent geological processes that have modified the surface over the past few billion years, even as large-scale volcanism ceased. These processes include the continuous rain of micrometeorites that slowly breaks down surface rocks into the fine-grained regolith that blankets most of the lunar surface, a process called space weathering that alters the optical properties of surface materials over time. Space weathering tends to darken lunar surfaces and reduce their spectral contrast, making fresh materials appear different from materials that have been exposed to space for long periods. The crew might observe variations in surface brightness that reflect differences in space weathering, with fresher craters appearing brighter than their surroundings and older surfaces appearing darker and more uniform. These brightness variations contain information about the ages of different surface features, though extracting that information requires careful calibration and comparison with laboratory studies of returned samples. The thermal environment of the lunar far side presents challenges for both human and robotic visitors that Artemis II will experience to a limited degree during its transit. Without an atmosphere to moderate temperature extremes, the lunar surface experiences swings from approximately 127 degrees Celsius in direct sunlight to negative 173 degrees Celsius in shadow. These extremes place severe demands on spacecraft thermal control systems, requiring careful management of heat rejection and thermal insulation. The brief duration of the Artemis II far-side transit means the crew will not experience the most extreme thermal challenges that a longer surface stay would present, but their spacecraft systems will nonetheless demonstrate operation in an environment quite different from low Earth orbit. The thermal data collected during the mission will inform the design of future missions that must operate for longer periods at lunar distance, missions that might include extended stays on the lunar surface or in stable orbits around the Moon. The communication challenge posed by the far side has driven development of solutions that will enable future missions to maintain contact with Earth throughout their operations. The most significant of these solutions involves relay satellites positioned at locations where they can simultaneously see both the Earth and the lunar far side, bridges across the electromagnetic shadow cast by the Moon's bulk. The physics of orbital mechanics provides several options for positioning such relay satellites, including the Lagrange points where gravitational forces from Earth and Moon create relatively stable positions for spacecraft. The second Earth-Moon Lagrange point, located beyond the Moon as seen from Earth, offers a particularly favourable location for relay satellites that could provide continuous coverage of the far-side surface. China has already demonstrated this capability with the Keqiao relay satellite that supports the Chang'e 4 mission, proving that far-side communication is technologically feasible with current systems. Future missions planning extended far-side operations will require similar relay infrastructure whose development the Artemis program is actively advancing. The geological history preserved on the lunar far side extends back to the Moon's earliest formation, a period so ancient that no comparable record survives anywhere on Earth. The lunar highlands that dominate the far side surface formed during the final crystallization of the magma ocean that covered the early Moon, a global sea of molten rock perhaps hundreds of kilometres deep. As this magma ocean cooled, minerals with different densities separated, with denser materials sinking toward the interior and lighter materials floating toward the surface to form the original lunar crust. The mineral anorthosite, composed primarily of plagioclase feldspar, was among the lightest of these materials, and accumulated at the surface to form the bright highland regions that remain visible today. The process of crustal formation from a magma ocean represents a fundamental stage in the evolution of rocky bodies throughout the solar system, a stage that the Moon preserves in remarkable detail because subsequent geological activity has been minimal compared to larger, more active worlds like Earth. The timeline of magma ocean crystallization carries implications for understanding the Moon's thermal evolution and the heat sources that have driven lunar geological activity. The initial heat that melted the Moon came from the energy of its formation, most likely the giant impact between Earth and a Mars-sized body, whose debris accumulated to form the lunar body. This impact released enough energy to completely melt the accumulating material, creating conditions for the differentiation that separated the Moon into distinct layers. The rate at which the magma ocean subsequently cooled depended on factors including the initial temperature, the insulating effects of surface solidification, and the heat released by crystallization itself. Models of this cooling process suggest it may have taken tens of millions to hundreds of millions of years, a period during which the Moon transitioned from a globally molten state to a solid body with a solidified crust and a still hot interior. The evidence for this timeline comes from isotopic dating of lunar samples returned by the Apollo missions, and from remote sensing observations of surface composition that can be compared with model predictions. The relationship between the Moon and Earth during and immediately after this period remains a subject of active research that far-side observations might inform in unexpected ways. The Moon formed much closer to Earth than its current distance, perhaps only about 15 to 20,000 kilometers away compared to the current average distance of approximately 384,000 kilometers. At this proximity, the Moon would have appeared enormously large in Earth's sky, and tidal forces between the two bodies would have been immensely stronger than today. These tidal forces gradually transferred rotational energy from Earth to the Moon, slowing Earth's rotation and pushing the Moon to greater distances. The process continues today at a rate of approximately 3.8 centimeters per year, a recession that will eventually cease when Earth and Moon become tidally locked to each other, with both showing the same face to the other at all times. The record of this orbital evolution might be preserved in lunar geological features, though extracting that record requires detailed understanding of how tidal forces affected the Moon's thermal and mechanical evolution. The far side highlands contain impact craters from all periods of lunar history, a record of bombardment extending from the earliest post-formation era through the heavy bombardment period and into the more quiescent recent past. The density and size distribution of these craters provide information about the impact of populations that struck the Moon at different times, populations that reflect the overall evolution of the inner solar system. Early in solar system history, debris left over from planetary formation filled the inner solar system, creating high impact rates that gradually declined as this material was swept up by planets or ejected from the solar system entirely. The impact record preserved on the lunar surface documents this decline, showing the transition from intense early bombardment to the much lower impact rates of the present day. The chronology derived from crater counting forms the foundation for dating surfaces throughout the inner solar system, a relative dating system calibrated by the absolute ages of lunar samples returned by Apollo. The far side craters contribute to this chronology, their preservation providing examples from periods and environments that the Apollo samples do not directly represent. The composition of far side crater floors and ejecta blankets reveals information about the subsurface materials excavated by impacts, materials that vary depending on where on the Moon the impact occurred and how deeply it penetrated. Some large craters have excavated through the surface and orthosite crust into underlying materials with different compositions, creating natural exposures of rock types that otherwise lie buried and inaccessible. The spectroscopic signatures of these exposures can be measured from orbit, revealing variations in iron content, titanium abundance, and mineral assemblages across the far side surface. These compositional variations map out the structure of the far side crust and possibly the underlying mantle, providing ground truth for models of lunar interior structure derived from gravity measurements and seismic data. The crew of Artemis II will observe some of these compositional variations as differences in surface color and brightness, visual characteristics that correspond to the chemical differences detected by orbital spectrometers. The human eye, trained by a lifetime of observing terrestrial landscapes, possesses remarkable sensitivity to subtle variations in hue and texture. The astronauts will perceive gradations of grey and brown and tan that cameras struggle to capture with the same fidelity, nuances of surface character that reveal themselves most clearly under the changing illumination conditions of their flyby trajectory. As Orion sweeps behind the Moon, the crew will watch shadows lengthen and contract across crater floors, see ridgelines catch the slanting light in ways that emphasize topographic features invisible in overhead imagery. Observe the interplay of brightness and darkness that gives three-dimensional form to a landscape seen from hundreds of kilometers above. This direct visual observation, reported in real time through the crew's descriptions and later through their detailed recollections, will supplement the instrument data with qualitative insights that no automated system can provide. The astronauts will notice things that mission planners did not anticipate, will ask questions that ground controllers had not considered, will bring to the observation the uniquely human capacity for pattern recognition and aesthetic appreciation that has driven scientific discovery throughout history. The moment of closest approach to the lunar surface during the far side passage will occur in relative silence as far as Earth communication is concerned. The Moon's bulk will block all direct radio transmission, leaving the crew temporarily isolated from the voices of mission control, alone with the ancient landscape rolling beneath them and the star-filled blackness above. This period of communications blackout, lasting approximately 47 minutes during the far side transit, represents one of the most psychologically significant aspects of the mission. For nearly an hour, the 4 astronauts will be the most isolated human beings in existence, separated from all of humanity not merely by distance, but by the complete impossibility of communication. No radio wave, no laser pulse, no signal of any kind can reach them or return from them during this interval. They will be utterly alone with the Moon. Previous Apollo astronauts who experienced this isolation described it in terms ranging from profound peace to mild unease, each responding to the solitude according to their temperament and circumstances. Jim Lovell, who experienced the far side passage during both Apollo 8 and the harrowing Apollo 13 mission, spoke of a strange tranquility that descended during the communications blackout, a quieting of the constant chatter that normally filled the spacecraft. William Anders described looking out at the far side during Apollo 8's blackout period and feeling an almost religious sense of awe at the desolation below, the most ancient and untouched landscape any human had ever witnessed. Michael Collins, orbiting alone in the command module while Armstrong and Aldrin walked on the surface during Apollo 11, experienced the far side isolation differently, aware that he was the most solitary human being who had ever lived during those minutes, when the Moon blocked all contact with both his crewmates and Earth. The Artemis II crew will add their own experiences to this small collection of testimonies, 4 more human perspectives on what it means to be completely alone with the Moon. The psychological preparation for this isolation forms part of the extensive training the crew has undergone in the years leading to launch. Unlike the Apollo astronauts who had only months to prepare for their lunar missions, the Artemis II crew has had years to contemplate every aspect of the flight, including the profound isolation of the farside passage. They have discussed the experience with the surviving Apollo veterans, gaining insights that no simulation can provide. They have practiced maintaining focus and operational efficiency during simulated communication blackouts, ensuring that the silence does not distract them from the observational tasks that must continue, regardless of whether anyone on Earth can hear their reports. They have explored their own psychological responses to isolation through various training exercises, building the self-awareness and coping strategies that will serve them during the real event. When the moment arrives and the radio falls silent, they will be as prepared as any human beings can be for the experience of absolute solitude in the cosmos. The scientific instruments aboard Orion will continue operating throughout the blackout period, recording data that will be transmitted to Earth once communication resumes. The cameras will photograph the landscape below according to predetermined sequences, capturing images that the crew can later describe and contextualize based on their real-time observations. Radiation sensors will measure the flux of charged particles reaching the spacecraft, documenting any variations associated with the Moon's position between Orion and the Sun, or with passage through regions of localized magnetic anomaly. The spacecraft's navigation systems will continue tracking position and velocity with extreme precision, using star trackers and inertial measurement units to maintain attitude awareness, even without communication with Earth. All of these automated functions will proceed without interruption, indifferent to the psychological weight of the isolation that their human passengers experience. But the scientific value of the mission extends far beyond instrument readings and camera images. The crew themselves represent the most sophisticated observational system ever sent to the vicinity of the Moon. 4 trained observers with the capacity to notice, interpret and remember details that no predetermined observation plan could anticipate. Their written notes, their voice recordings made during the blackout for later transmission, their memories that will be debriefed exhaustively after return, all of these constitute scientific data of irreplaceable value. The human brain processes visual information with a sophistication that no artificial system matches, recognizing patterns, detecting anomalies, forming hypotheses in real time based on the accumulated knowledge and intuition of a lifetime. When one of the astronauts notices something unexpected about the far side landscape, something that does not quite match the predictions or the previous observations, that moment of human perception may prove more valuable than terabytes of instrument data. The far side observations will contribute to several major categories of ongoing lunar research, each addressing questions that have remained partially unanswered since the Apollo era. The first category concerns the Moon's internal structure, the arrangement of layers from surface crust through mantle to core that determines how the Moon responds to impacts, how it has evolved thermally over billions of years, and how it differs fundamentally from Earth despite their common origin. The far side crust appears significantly thicker than the near side crust, an asymmetry first detected through variations in how spacecraft orbits change as they pass over different regions. This crustal thickness variation correlates with the hemispheric dichotomy in volcanic activity, suggesting a deep connection between interior structure and surface geology that models of lunar evolution must explain. Visual observation of the far side terrain may reveal structural features associated with this crustal thickness variation, subtle indications of how the crust has responded to stresses generated by the underlying mantle. The second category concerns the impact history of the inner solar system, the chronology and intensity of bombardment that the Moon has recorded more faithfully than any other accessible body. The far side preserves the oldest and least modified impact record anywhere within reach of human exploration. Craters from the earliest post-formation era sitting relatively undisturbed on a surface that has not been flooded by lava or fractured by major tectonic events. The age distribution of these craters, inferred from their degradation state and from the density of smaller craters superimposed on their floors and walls, provides the calibration against which all other inner solar system surfaces are dated. Visual observation can contribute to this chronology by noting the preservation states of craters across different far-side regions, identifying areas of particularly ancient or particularly well-preserved terrain that might warrant future detailed study. The third category concerns the distribution and origin of volatile compounds on the lunar surface, particularly water ice, and the complex organic molecules that may accompany it. The far-side permanently shadowed regions represent some of the coldest and most stable volatile traps anywhere in the inner solar system. Environments where water molecules delivered by comet impacts or created by solar-wind interaction may have accumulated over billions of years, while Orion's trajectory will not bring the crew directly over the south polar regions, where the largest permanently shadowed craters exist. The far-side passage will provide views of terrain at high southern latitudes where smaller shadowed regions may also contain volatiles. The visual appearance of these regions, particularly any differences in colour or texture, compared with sun-exposed terrain, may provide clues about volatile distribution that complement the data from dedicated polar missions. The fourth category, and perhaps the most profound, concerns the Moon's relationship to the early history of life on Earth. The period between approximately 4.1 and 3.8 billion years ago, known as the Late Heavy Bombardment, saw a dramatic increase in the rate of large impacts throughout the inner solar system. The cause of this bombardment spike remains debated, with explanations ranging from destabilization of asteroid orbits by giant planet migration to delayed effects of solar system clearing. The consequences for Earth may have been severe, with some researchers suggesting that the bombardment repeatedly sterilized Earth's surface, eliminating any early life that had emerged and forcing life to restart from hydrothermal vent environments or other protected refugia. Other researchers argue that the bombardment was less intense than previously thought, that life could have survived through even the largest impacts, that the bombardment might actually have delivered organic molecules and water that enhanced Earth's habitability. The lunar far side preserves the clearest available record of this bombardment period, craters from the bombardment era that have not been obscured by subsequent geological activity. Understanding the true intensity and duration of the late heavy bombardment requires detailed study of lunar surfaces like those the Artemis II crew will observe, surfaces that document the violence or relative calm of the era when life first emerged on Earth. These four categories do not exhaust the scientific potential of far-side observations. The regolith gardening process, the constant churning of surface material by micrometeorite bombardment, operates differently on the far side than on the near side due to differences in the charged particle environment and possibly in the micrometeorite flux itself. The magnetic anomaly regions concentrated on the far side represent a puzzle whose solution may require direct observation of the terrain they overlie, terrain whose appearance might differ subtly from magnetically quiet regions due to enhanced solar windshielding or other effects. The thermal properties of far-side materials, how quickly they heat and cool as the sun rises and sets, provide information about surface texture and composition that visual observation can supplement by noting variations in appearance under different lighting conditions. Each of these secondary questions might yield to insights triggered by crew observations, moments when a trained eye notices something that previous missions missed. The return from behind the moon will bring its own moment of significance. As Orion's trajectory carries it around the western limb, Earth will rise above the lunar horizon, initially as a sliver of blue and white against the absolute blackness of space, then as an ever larger disk as the spacecraft continues its swing back toward home. The astronauts will witness what Apollo 8 first revealed to human eyes, the vision of Earth as a small, fragile sphere hanging in the void, a revelation that fundamentally changed human consciousness when the famous Earthrise photograph reached the public in December 1968. The Artemis II crew will capture new versions of this iconic image, photographs showing Earth rising over a cratered far-side horizon, the contrast between the living world and the dead moon rendered in colours and details that modern camera technology will record with unprecedented fidelity. These images will serve not only as scientific data but as cultural touchstones, reminders of the perspective that only space exploration can provide, the humbling recognition of Earth's isolation and preciousness that has become one of the most important outputs of the space age. The communication restoration will be sudden. As Orion's antenna array regains line of sight to Earth, the radio will crackle with the voices of mission control, re-establishing the link that connects the crew to the entire human race. The first words spoken after the blackout period will be recorded and remembered, joining the small collection of phrases that define pivotal moments in spaceflight history. The crew will report their status, confirm that all systems performed nominally during the unsupervised interval, and begin transmitting the data recorded during the far side passage. The scientific returns will begin flowing to Earth immediately, images and readings that analysts will study for years to come, but the most valuable data may be the crew's verbal descriptions of what they observed, the nuances and impressions that fill the gaps between instrument measurements. The journey home from lunar distance requires approximately 6.5 days, a span during which the crew will have ample time to reflect on what they have witnessed and to prepare for the technical challenges of Earth re-entry. The Orion spacecraft will use its service module engine to refine its trajectory, ensuring that the re-entry angle falls within the narrow range that produces a safe landing. Too steep an angle would subject the crew to excessive deceleration forces and heat the heat shield beyond its design limits. Too shallow an angle could skip the spacecraft off the upper atmosphere, sending it into an orbit that might not allow recovery. The target corridor is only about 40 kilometers wide at the point where the spacecraft touches the atmosphere, a precision that requires continuous navigation updates throughout the return transit. The crew will monitor these updates, confirming that the autonomous systems are performing correctly and standing ready to intervene if any anomaly threatens the re-entry profile. The heat shield that will protect the crew during re-entry represents one of the most critical technologies developed for the Artemis program. Unlike the re-entry shields used by spacecraft returning from low Earth orbit, which dissipate relatively modest amounts of energy, the Orion heat shield must survive velocities approaching 40,000 km per hour, speeds that generate temperatures exceeding 2,700 degrees Celsius on the shield surface. The material, a proprietary ablative compound called AVU coat, functions by absorbing heat through controlled vaporization, carrying thermal energy away from the spacecraft as it erodes. The shield is manufactured in sections and hand-applied to the spacecraft structure, a labour-intensive process that reflects the critical importance of perfect protection during the most dangerous phase of the mission. The Artemis II re-entry will provide the first crewed test of this heat shield at lunar return velocities, validating its performance under conditions that no uncrewed test can fully simulate. The splashdown in the Pacific Ocean will mark the successful conclusion of the mission, but not the end of the scientific returns. The crew will undergo extensive medical examinations to document the effects of their 10-day exposure to deep space radiation and microgravity, data that will inform health planning for the longer Artemis missions to follow. The recorded observations and imagery will be processed and distributed to the scientific community, triggering analysis efforts that may continue for decades. The spacecraft itself will be recovered and studied, its systems examined for any signs of degradation or unexpected performance that might affect future missions. The far-side observations that seemed so ephemeral during the brief passage behind the Moon will take permanent form in databases and publications and mission reports, contributions to human knowledge that will outlast everyone alive to witness the mission itself. But perhaps the most important legacy of Artemis II will be what it represents, rather than what it discovers. For 53 years, no human being has travelled beyond low Earth orbit. Generations have grown to adulthood, knowing the Apollo missions only as history, as footage and photographs from an era before their birth. The humans who actually walked on another world have dwindled to a single elderly survivor, Buzz Aldrin, who was already in his 40s when he stepped onto the Sea of Tranquility. The experience of travelling to the Moon has existed only in memory, a fading recollection held by an ever smaller group of aging men and their increasingly distant listeners. Artemis will make that experience present tense again, a living reality rather than a historical artefact, a thing that is happening rather than a thing that happened. The 4 astronauts aboard Orion will see what Harrison Schmitt saw when he looked out at the far side during Apollo 17's return journey in December 1972, the last human eyes to observe that landscape until now. They will know what the Apollo astronauts knew about the isolation and the scale, and the ancient stillness of the Moon, knowledge that no amount of reading or simulation can provide. They will return to Earth changed by what they have witnessed, as every Apollo astronaut was changed, carrying perspectives that will influence their words and actions for the rest of their lives. And through them, through their descriptions and images and testimony, something of that perspective will reach all of humanity, a reminder of what we are capable of when we choose to reach beyond the familiar world. The far side of the Moon has waited patiently through all the decades of human absence, its craters and basins and highlands unchanging under the distant sun, its ancient surface accumulating only the slow rain of micrometeorites that has fallen for billions of years. It has witnessed no drama, experienced no anticipation, remained as indifferent to human observation as it was during the eons before life existed on the blue planet that hangs forever hidden below its horizon. The rocks that the Artemis II crew will observe are the same rocks that the Apollo astronauts glimpsed a half-century ago, unchanged in every meaningful way, monuments to the timescales on which planetary geology operates, compared with the brief flicker of human history. Yet for us, for the beings who look up at the night sky and wonder what lies beyond, the far side holds meaning that its rocks cannot contain. It represents the frontier, the edge of direct human experience, the boundary between the known and the unknown. Every scientific question it poses, every mystery its ancient surface encodes, exists because human minds have learned to formulate such questions, to recognize mystery where once there was only ignorance. The Moon does not care whether we understand it. We care. And that caring, that restless drive to see and know and understand, is what sends us across the void to look upon landscapes that have no need of our attention. The crew of Artemis II will spend only a few hours behind the Moon, a brief transit measured against the billions of years that surface has existed. They will capture images, record observations, describe what they see in voices that will be heard by millions when communication resumes. Then they will swing back around the western limb, watch Earth rise over the lunar horizon, and begin the journey home carrying data and memories that will take years to fully process and centuries to fully appreciate. The far side will recede behind them, returning to its ancient solitude, waiting for the future missions that will eventually land astronauts on its surface and begin the permanent human presence that Artemis is designed to enable. The questions that the far side poses, questions about planetary formation and impact history and the origins of water and the nature of ancient magnetic fields, will not be answered by this single flyby. They will be advanced incrementally, as every scientific question is advanced, through observation, through analysis, through the slow accumulation of evidence that eventually resolves uncertainty into understanding. The Artemis II far-side observations represent one small step in this process, a contribution to a scientific edifice that has been under construction since Galileo first turned his telescope toward the Moon in 1609 and will continue rising as long as humans retain the capacity to wonder. But small steps accumulated carry us to destinations that would be impossible to reach in a single leap. The Moon itself lies 384,000 kilometers from Earth, a distance that seems vast until you consider that early humans, walking at 5 kilometers per hour, could have covered that distance in approximately 8.5 years of continuous travel. We did not walk to the Moon. We built machines that carried us there in 3 days, machines whose development required thousands of small steps in physics and engineering, and materials science and rocketry, each step seeming modest in isolation, all of them together constituting the greatest technological achievement in human history. The scientific understanding of the Moon will be built the same way, through missions that each seem limited in scope, observations that each seem to address only narrow questions, until one day we look back and realize that we have come to understand this world that orbits our own, this companion that has watched over Earth's nights since before life emerged from the primordial oceans. The far side keeps its counsel, patient and eternal, its craters filled with shadows that have never known illumination, its highlands bright with the reflected light of a sun that sets and rises on a schedule no human has ever witnessed continuously. In a few weeks, 4 human beings will look upon this landscape with their own eyes, will describe what they see in words that will echo through the media of the world, will capture images that will become iconic representations of humanity's return to deep space. Then they will come home, and the far side will wait again, as it has always waited, for the next visitors who will follow the path that Artemis II is about to blaze. The Moon asks nothing of us. It simply exists, a world unto itself, indifferent to observation and interpretation. But we cannot help asking questions of it, cannot help seeking to understand the story written in its rocks and craters and the geometry of its orbit. This is what it means to be human, to look at the unknown and feel compelled to know it, to stand on the shore of ignorance and build boats that carry us toward comprehension. The far side of the Moon is one such shore, and Artemis II is one such boat, fragile and temporary and precious beyond measure. The crew members training for this mission understand what they represent. They are not simply astronauts performing a technical demonstration. They are the first of a new generation of lunar explorers, the inheritors of a legacy that began with Apollo and was interrupted for reasons both budgetary and political. They carry the hopes of everyone who has looked at the Moon and wondered what it would be like to travel there, everyone who has read about the Apollo missions and wished they had been born early enough to witness them, everyone who understands that human destiny lies among the stars, and that the Moon is merely the first way station on that infinite journey. When they look out the windows of Orion at the far-side landscape scrolling beneath them, they will see it not only for themselves but for all of us, the billions who remain bound to Earth while they make this journey on humanity's behalf. The ancient rocks below will not notice their passage. The craters will not shift to provide better viewing angles. The far side will remain exactly as it has been for billions of years, changeless and silent, and magnificently indifferent to the small vessel carrying 4 curious primates around the back of a world they cannot even see from their home planet. But those curious primates will notice everything. They will look and describe and record, will bring back data and images and memories that will enrich human understanding of this universe we inhabit. And that is enough. That is, in fact, everything. The story of Artemis II is ultimately not about the Moon. It is about us, about the species that evolved on a small rocky planet and developed the intelligence and ambition to leave it. The far side is merely the backdrop, the stage upon which this act of the human drama will unfold. What matters is that we are going, that we have chosen to reach beyond the familiar, that we have decided the questions are worth asking even when the answers remain uncertain. The moon will keep its secrets or yield them according to physics and probability, not according to human desire. But we will keep asking, keep looking, keep sending our representatives to places no human has ever been, because that is who we are. The far side awaits. The mission is nearly ready. And when Orion sweeps behind the moon and the radio falls silent, and the crew looks out at that ancient, battered, magnificent landscape, they will see what humans have not seen in half a century. The hidden face of our nearest neighbour. The dark side of the only world humanity has ever touched. They will see it, and they will tell us what they found, and we will all be richer for the knowledge. The universe is vast beyond comprehension, and we are small beyond significance, but we can reach out and touch other worlds, can send our senses and our instruments and eventually our bodies to places the cosmos never expected to be observed. That is the miracle. That is what Artemis II represents. Not merely a mission, not merely a technical demonstration, but a reaffirmation of what makes humanity worth preserving. The endless, restless, magnificent drive to understand.